Hello there and welcome to Science for Sleep, where curiosity gets cozy, the universe slows down just a little, and even the Milky Way is allowed to stretch out and relax for the evening. Tonight, we are drifting into one of the strangest nearby structures astronomers have ever found. Not a planet, not a star, not a black hole with dramatic table manners, but a vast wave of gas and dust lying close to our own solar neighbourhood. It is called the Radcliffe Wave, and it is so large that if we could step far outside the Milky Way, turn around and look back with patient eyes, we might see our local part of the galaxy not as a neat flat road, but as something with a bend in it. A long wavering chain of star-forming clouds, rising and falling through the galactic disk like a slow ripple in an enormous pond. And the odd thing is, for a very long time, we did not know it was there. That is perhaps the most quietly wonderful part of this story. The Radcliffe Wave is not some distant object hiding billions of light years away, far beyond the reach of our daily imagination. It is part of the neighbourhood. It is close enough, in galactic terms, to be considered local. It runs through regions of the Milky Way connected with famous stellar nurseries, places where gas gathers, cools, collapses, and begins the long process of making new stars. The Orion region, for instance, that familiar winter landmark many people have seen without needing a telescope, is part of the wider story. So are other great cloud complexes scattered across the sky. They were known individually for generations. Astronomers had catalogued them, studied them, photographed them, measured them, argued politely about them, and probably made many very serious diagrams about them. But only recently did the bigger shape begin to emerge. The pieces were not just random nearby clouds, they were part of a single huge arrangement. It is a little like living beside a coastline your whole life, walking past cliffs and coves and beaches one at a time, and then one day seeing an aerial map and realizing the whole shore curves into a great sweeping bay. Nothing new appeared. The rocks were always there. The water was always there. But the pattern was too large to notice from the ground. So before we wander into this giant wave together, let me ask you something gentle. Where are you listening from tonight? Are you near a city window with traffic murmuring outside, somewhere quiet with the room already dark, or tucked into bed while the rest of the house settles down around you? And when you look up at the night sky, if you can see it from where you are, do you ever get the feeling that our solar system is not simply sitting in empty space, but floating through a neighbourhood with structure, weather, history, and a few surprises tucked behind the familiar stars? Because that is where tonight's story begins. Not with a single bright object, but with a new way of seeing where we are. If you find this kind of slow, cosmic wandering soothing, or if it gives your thoughts somewhere calm to rest after a long day, I would be very grateful if you gave the video a like and subscribed. It helps this small, sleepy corner of science reach other curious people who might also enjoy falling asleep somewhere between a gas cloud and a question. And if you are already getting comfortable, do not worry. The Radcliffe Wave has been waiting millions of years. It will not mind if your eyelids get heavy before we finish. Now, settle in. Let your shoulders loosen. Let the room become ordinary and peaceful around you. We're going to take something that sounds almost impossible, a giant wave near the sun, and unfold it slowly, piece by piece, until it becomes not just a headline, but a place. A real structure in our galaxy. A long trail of cold gas and stellar nurseries. A shape so large that our ancestors could see parts of it in the sky without ever knowing those parts belonged together. At first, the phrase itself can feel a bit confusing. A giant wave surrounding our solar system sounds as if the sun is sitting inside a cosmic ocean swell, perhaps with Jupiter wearing a tiny life jacket and Saturn politely asking whether anyone brought towels. But the Radcliffe Wave is not a wave of water, and it is not crashing toward Earth. It is not a dangerous wall moving through space like something from a disaster film. It is a vast structure made mostly of interstellar gas and dust, the raw material from which stars can form. It curves through the Milky Way near our solar system, stretching across a huge region of the sky, weaving together several star-forming clouds that once seemed separate. In other words, this is not a wave you surf, it is a wave you map. And mapping the Milky Way from inside the Milky Way is not easy. We are not looking at our galaxy from above, the way we see beautiful images of spiral galaxies in astronomy books. We are embedded in it. We are inside the disk, surrounded by stars, gas, dust, and distance. Trying to understand the shape of the galaxy from Earth is a bit like trying to understand the layout of a forest while standing among the trees at night with a flashlight. You can see trunks nearby. You can guess at clearings. You can notice where the branches thicken. But the full pattern is hidden from your position. For a long time, astronomers believed that many nearby star-forming clouds might be part of a structure called the Gould Belt, a kind of tilted ring of young stars and gas around the Sun. It was a useful idea, and it helped organise what astronomers could see. But useful ideas in science are not permanent furniture. They are more like chairs we sit in until someone builds a better one. As distance measurements improved, and as three-dimensional maps of dust became more detailed, the old picture began to change. What had once looked like a ring began to look like something else. Not a belt around us, but a long, narrow, wave-shaped structure passing through the local region of the galaxy. The name Radcliffe Wave comes from the Radcliffe Institute, connected with the Harvard environment where the discovery took shape. It is a very calm name for something enormous. It sounds almost like it should be a walking path beside a college garden, perhaps with benches and someone reading quietly under a tree. But in this case, the path is thousands of light years long, made of clouds cold enough and dense enough to help form stars, and arranged in a pattern that rises and dips through the Milky Way's mid-plane. A gentle academic name, then, for a structure big enough to make the local galaxy seem less flat than we imagined. The scale takes a little patience to absorb. We are used to thinking of our solar system as large, and it is. Light from the Sun takes about 8 minutes to reach Earth, several hours to reach the outer planets, and much longer to move into the colder outskirts beyond Neptune. That already feels immense. But the Radcliffe Wave belongs to a different level of size altogether. It stretches for thousands of light years. A light year is the distance light travels in 1 year, and light is not exactly dawdling. It moves fast enough to circle Earth several times in a single second. So when something is thousands of light years long, it is not merely big, it is galactic furniture, and our Sun is nearby. Not sitting directly in every part of it, of course, but close enough that this structure belongs to our broader neighbourhood. That is what makes it so interesting. We are not only learning about a distant spiral arm feature somewhere far across the Milky Way. We are learning about the environment around the Sun, the gas structures near us, the star-forming history of our region, and possibly even the larger pattern that helps explain why certain famous nebulae and molecular clouds appear where they do. There is something humbling about that. We often imagine discovery as a matter of looking farther away. Build a bigger telescope, see deeper space, find a galaxy closer to the beginning of time. And yes, that is one of astronomy's great adventures. But sometimes discovery means looking more carefully at home. It means measuring distances better. It means taking familiar objects and placing them correctly in 3 dimensions. It means realizing that the sky is not a flat picture pasted above us, but a layered, folded, textured environment. Think of the night sky for a moment. From Earth, stars and nebulae appear projected onto a dome. Orion sits over there, Taurus over there, Cygnus in another direction, Cepheus elsewhere. To our eyes, these are patterns on the ceiling of night, but in reality every point of light has depth. Some stars are close, some are far, some clouds are in the foreground, others are behind them, dust blocks light, redden stars and hide structures. If we only know the direction of something, we have a beautiful sky map, but not a true 3-dimensional one. The Radcliffe Wave emerged because astronomers could begin to measure not only where dusty clouds appeared on the sky, but how far away they were, That was the key. Distance changed the picture. Modern astronomy has become very good at turning scattered measurements into maps. Space missions like Gaia have measured the positions and motions of enormous numbers of stars with extraordinary precision. When astronomers combine that with observations of starlight dimmed and reddened by dust, they can infer where dust clouds lie between us and those stars. It is almost like using millions of tiny background lamps to trace fog in a dark field. If a star looks dimmer or redder than expected, there may be dust in front of it. If many stars at known distances show a pattern of dimming, the dust begins to take shape, and with enough stars, enough patience, and enough computing power, that shape becomes a three-dimensional map. This is where the hidden coastline appears. Once the distances to nearby molecular clouds were mapped with more confidence, the familiar local star-forming regions no longer looked like separate islands. They lined up. They formed a long arrangement. They traced a wave. The Radcliffe Wave was not discovered because someone saw it glowing as a single object in the night sky. It was discovered because data revealed that many known clouds were connected in space. The discovery was not a sudden flash, but a reorganization of understanding. The map changed, and with it, the neighborhood changed. That is one of the quiet joys of science. Sometimes the universe does not add anything new. It simply says, look again. And when we look again, we find that our solar system is moving through a galaxy full of structure. The sun is not fixed. It orbits the center of the Milky Way, carrying Earth and all the planets along with it. Our whole solar system is traveling through this galactic disk, passing through regions of different density, different gas, different dust, different stellar populations. The Milky Way is not a painted backdrop. It is a moving environment. Stars orbit, gas flows, clouds gather, supernova carve bubbles, spiral arm shift material, gravity pulls and stirs. Over millions of years the solar neighborhood changes. The Radcliffe Wave fits into that larger picture. It reminds us that the local galaxy is not simply a calm, flat sheet of stars. It has ripples, it has filaments, it has old scars and fresh nurseries. It has shapes that may be connected to gravity, galactic motion, feedback from massive stars, or events we have not fully reconstructed yet. There are still open questions. What made the wave? Has it always had this shape? Is it part of the Orion Arm structure? How does it move? Did the sun pass near or through material related to it in the past? Could such passages affect the flow of interstellar dust into the solar system? These are not bedtime questions in the sense of being simple, but they are bedtime questions in the better sense. They are large enough to let the mind wander gently without needing every answer at once. And recently the story became even more interesting. The Radcliffe Wave does not only seem to look like a wave, evidence suggests that it may also move like one, oscillating through the plane of the Milky Way while drifting outward from the galactic center. That does not mean the whole structure is sloshing quickly in a way we could notice from Earth. Galactic motion is slow by human standards, even when the speeds are enormous. The timescales are vast. The wave is not doing a dramatic splash. It is more like a long, slow movement written across millions of years. A stadium wave is one comparison scientists have used, though in this stadium the fans are molecular clouds, young stars and gravity, which admittedly makes buying snacks between innings more complicated. Still, the idea is wonderfully concrete. A structure made of gas rises and falls through the galactic disk. Regions along it form stars. Those stars carry information about motion. Gas velocities add another layer. Put the pieces together, and astronomers can ask whether the shape is merely wave-like, or whether it has the motion of a wave as well. That distinction matters. A rope lying on a table can be curved like a wave without actually waving. But if the rope is moving up and down, then the shape is not just geometry. It is behavior. It is history and motion. The Radcliffe Wave may help astronomers measure aspects of the local galactic environment, because its movement is influenced by the Milky Way's gravitational field. That is a very practical use for something that sounds so dreamy. The wave becomes not just an object to admire, but a tool. By studying how it moves, scientists can learn about the mass distribution near the Sun and the way the galactic disk behaves. It is rather like watching how a floating leaf moves on a pond to infer the currents underneath. The leaf is not the whole pond, but its motion gives clues. Of course, science is careful. One study opens a door, another checks the hinges, and others come along with different tools to see whether the door is where everyone thinks it is. The Radcliffe Wave is still being studied, and not every detail is settled. That is normal, and honestly, rather comforting. A new galactic structure should not be expected to hand over all its secrets immediately. It has had millions of years to become complicated. We can allow astronomers more than a few afternoons to sort it out. What matters for our story tonight is that the Radcliffe Wave changes the way we picture our surroundings. It shows that even the region around the Sun has large-scale architecture. We are not drifting through a simple blank gap between famous objects. We are near a long, structured chain of star-forming material, a feature that connects familiar regions into a larger whole. The night sky is not only a collection of separate wonders, it is a map of relationships waiting to be understood. So as you rest here, perhaps with your eyes half closed, imagine shrinking the solar system down to a tiny point and lifting your view above the Milky Way. The Sun becomes a small marker in the local arm. Around it, the galaxy's disk spreads wide, full of stars and dark lanes of dust. Nearby, a long wave of dense gas bends through space, crossing regions where new stars are forming. It is not bright like a neon sign. It does not announce itself to casual eyes, but with the right measurements it appears, a hidden structure nearby all along, connecting the Orion clouds and other stellar nurseries in a way we only recently understood, and perhaps that is the best way to enter the story, not with alarm, not with grand drama, but with the simple realization that our cosmic neighborhood has a shape we missed. The solar system is moving through a Milky Way that is layered, rippled, and alive with slow change. The Radcliffe Wave is one of those nearby features that reminds us how much of the familiar sky is still unfamiliar in 3 dimensions. We have looked upward for thousands of years, named constellations, told stories, built calendars, navigated oceans, and wished on stars. Yet only now are we beginning to see the local galaxy as a true landscape. Inside the Milky Way, the first difficulty is not that the galaxy is too dark to see. In many directions, it is almost too crowded. Stars pile into the view, dust dims the stars behind it, gas hides in wavelengths our eyes cannot detect, and everything sits at a different distance while appearing on the same flat sky. From Earth, the Milky Way does not politely present itself as a clear diagram with labels, arrows, and a helpful little note saying, "You are here." It surrounds us. It fills the background. It is the house, the street, the weather, and the map all at once, which makes studying it a bit like trying to understand the shape of your own blanket while you're still tucked underneath it. For centuries, people saw the Milky Way as a pale band across the night sky. Under dark skies, away from city lights, it looks like a soft streak of brightness spilled from horizon to horizon. Ancient cultures gave it many meanings. Some imagined it as a road, some as smoke, some as a river, some as the trace of something divine. Later, with telescopes, astronomers realized that the glow was not a smooth material at all, but the combined light of countless stars too close together for human eyes to separate. That was already a major shift. The cloudy band became a star field, the sky became deeper, the familiar night became less like a ceiling and more like a window. Yet even after astronomers understood that the Milky Way was made of stars, its full shape remained difficult to grasp. We now know it is a barred spiral galaxy, a disk of stars, gas and dust with a central bar and spiral arms winding outward. But we know that partly by combining many indirect clues. We cannot simply fly above the galaxy, take a photograph, and come back before breakfast. The Sun sits inside the disk about 26,000 light-years from the centre, embedded among stars, dust lanes, molecular clouds, and the local structures of the Orion Arm. So when astronomers try to map the Milky Way, they are not looking at a separate object. They are trying to reconstruct the body of a whale, while sitting inside one of its ribs, which is not recommended fieldwork, even with excellent funding. The view from inside creates a very specific problem. Direction is easy, distance is hard. If you look at a patch of sky and see a dark cloud, you know where it appears from your viewpoint. But you may not know whether that cloud is fairly close, moderately far, or part of a larger structure stretching away behind it. Two clouds can appear side by side even if one is hundreds of light-years closer than the other. Two stars can look like neighbours even if one is in our local region and the other is far across the galaxy. This is why constellations are beautiful but misleading. Orion looks like a familiar pattern, but its stars do not sit on a single wall. They are scattered through depth. The sky shows direction first, not distance. Dust makes the problem harder and also, strangely, helps solve it. Interstellar dust is made of tiny grains mixed with gas. It is not dust in the household sense, though the idea of the Milky Way needing a vacuum cleaner is not entirely unpleasant. These grains block and scatter starlight. Blue light is scattered more strongly than red light, so dust can make stars behind it appear dimmer and redder. For a long time, dust was a nuisance. It hid parts of the galaxy. It made distances harder to estimate. It turned clean star maps into puzzles with missing pieces. But once astronomers learned how to measure its effect carefully, dust became a tracer. If you know how far away many stars are, and you measure how much their light has been reddened, you can begin to infer where the dust lies between you and them. This is where modern astronomy quietly changed the story. Instead of treating the sky as a flat image, astronomers began building three-dimensional maps. They used star distances, star colours, brightness measurements, and statistical models to estimate where dust must be located in space. The European Space Agency's Gaia mission played a major role in this broader revolution, because it measured the positions and distances of huge numbers of stars with remarkable precision. A star's distance can be found through parallax, the tiny apparent shift in its position as Earth moves around the Sun. Hold up a finger in front of your face, close one eye, then the other, and your finger seems to jump against the background. Nearby stars do something similar against more distant stars, except the shift is so small that measuring it requires serious instruments, careful calibration, and a tolerance for numbers with many decimal places. Once Gaia improved the distances to many stars, astronomers had a better framework for locating the dust clouds in front of them. Imagine standing in a foggy field at night with thousands of lanterns placed at known distances. Some lanterns are clear, some are dimmed, some are reddened. By comparing all of them, you could begin to map where the fog is thickest. Now expand that idea to millions of stars, enormous computers, and the local region of the Milky Way. The result is not perfect, and it is not simple, but it gives astronomers something they never had before in such detail: a three-dimensional view of the dusty structures near the Sun. And when that view sharpened, something unexpected appeared. Many of the famous nearby star-forming clouds had long been treated as separate regions or as parts of a tilted ring-like structure around the Sun. The old idea was called the Gould Belt. It had a long history and was not foolish. From Earth, the distribution of young stars and gas did look like a tilted arrangement crossing the sky. Astronomers used it because it explained some of what they saw. Science often works this way. A model can be useful for a time, then become less useful when better measurements arrive. It is not a failure. It is more like replacing a slightly blurry pair of glasses with a clearer one, and suddenly noticing that the thing you thought was a ring is actually a long bend. The new map showed that several nearby molecular clouds lined up in a coherent structure. Taurus, Perseus, Orion, Cepheus, and other regions were not just scattered bits of local star formation. They traced a long, narrow feature with a wave-like shape. Instead of a belt around the Sun, the data suggested a gigantic filament, rising and dipping through the plane of the Milky Way. That structure became known as the Radcliffe Wave. It was not discovered because it suddenly shone brighter. It was discovered because the distances finally allowed the pieces to sit in the right places. This is a good moment to slow down and picture what a molecular cloud actually is. It is a cold, dense region of gas and dust, mostly hydrogen molecules, where the conditions can allow star formation to begin. These clouds are not solid objects. They are not neat puffs with tidy edges. They're irregular, turbulent, magnetized, lumpy, and often stretched into filaments. Parts of them can collapse under gravity. Dense pockets form. Young stars appear. Radiation and winds from those stars then disturb the surrounding gas, sometimes helping new stars form nearby, sometimes blowing material away. A molecular cloud is not a quiet warehouse of star ingredients. It is more like a slow, cold construction site, with gravity as the foreman and turbulence wandering around with a clipboard. The Radcliffe Wave is made from this kind of material. It is a chain of star-forming clouds, a large-scale arrangement in the local galaxy. From our position, these clouds are spread across different parts of the sky. Some are famous to amateur astronomers and astrophotographers. Orion is easy to love because it has bright stars and the Orion Nebula, a visible stellar nursery hanging below the belt of the constellation. Taurus contains dark clouds and young stars. Perseus has its own active regions. Cepheus, farther along the structure, hosts young stellar groups. Seen one by one, each cloud is interesting. Seen together in 3 dimensions, they become a feature. That difference between seeing pieces and seeing structure is important. Human brains are good at patterns, but only when we have the right perspective. If someone showed you 10 close-up photos of a coastline, one cliff here, one beach there, one harbour somewhere else, you might appreciate each image without realising they all form the edge of the same island. The Radcliffe Wave was a little like that. Astronomers had many close-ups. They had names, catalogues, measurements, and local stories. What they lacked was the full 3-dimensional arrangement at the necessary scale. The Milky Way's disk also adds another complication. We often imagine a spiral galaxy as a flat plate, perhaps because many illustrations show it that way. But a galactic disk is not perfectly flat like a dinner plate, and if it were, it would be a rather alarming dinner plate, 100,000 light-years across and difficult to wash. The disk has thickness. Stars bob above and below the midplane as they orbit. Gas can be disturbed by gravity, spiral structure, supernovae, magnetic fields, and encounters with smaller galaxies. The Milky Way itself has warps and ripples on large scales. So a wave-like structure near the Sun does not appear in a galaxy that is otherwise completely still and smooth. It appears in a system that is already dynamic. Still, the Radcliffe Wave was surprising because of its size and proximity. It is close enough to be part of our galactic neighbourhood, yet large enough that its full shape was hidden by perspective. That combination is the real trick. If something is very far away, we expect it to be hard to understand. If something is nearby, we assume we should know it well. But nearby does not always mean obvious. A mountain range can be harder to recognise when you live inside one of its valleys. You see slopes, ridges, and weather. The full curve of the range belongs to a map. This is why the phrase, "inside the Milky Way," matters so much. Our position gives us rich detail, but it steals the overview. We can measure individual stars in exquisite precision. We can study nearby clouds better than faraway clouds. We can observe the chemistry of gas, the motion of young stars, and the glow of dust in different wavelengths. But the large-scale arrangement is not handed to us. Astronomers have to assemble it, and every assembly depends on distance. Without reliable distances, a structure can be stretched, compressed, or invented by projection. With better distances, false patterns can disappear and real patterns can emerge. The old Gould belt picture is a helpful example of how projection can fool us. From Earth, a tilted ring of star-forming regions seemed plausible. It organised observations into a simple shape around the Sun. But the improved three-dimensional dust map suggested that many of those regions were instead aligned along the Radcliffe Wave. The Sun was not sitting neatly inside a ring of local stellar nurseries. It was near a long wave-shaped chain. That change is subtle in words but large in meaning. A ring makes us feel centred. A wave makes us part of a bigger flow. One places us near the middle of an arrangement. The other places us beside a structure passing through the local arm. There is a nice humility in that. Astronomy has repeatedly moved Earth away from the centre of things. Earth was not the centre of the solar system. The Sun was not the centre of the galaxy. The Milky Way was not the whole universe. And now, in a smaller but still meaningful way, the local star-forming regions around us are not necessarily arranged around us either. They have their own structure, and we happen to be nearby. The universe, with great consistency, refuses to organise itself for our convenience. It is very rude, but scientifically productive. To understand how astronomers found the hidden shape, it helps to think about layers of information. First, there is the two-dimensional sky, where clouds and stars have positions on the celestial sphere. Then there are distances, giving depth. Then there are motions, showing how objects move through space. Then there are ages, showing when young stars likely formed. Then there is chemistry, which can link regions by shared material or history. Each layer adds dimension to the story. The Radcliffe Wave first stood out through spatial mapping of dust and molecular clouds. Later, motion studies asked whether the structure was only shaped like a wave or whether it was actually moving in a wave-like way. But before motion, before causes, before the question of whether our solar system passed near it, there was the basic problem of recognition. Astronomers had to learn to see the local sky as a three-dimensional volume. That may sound simple, but it is one of those simple ideas that requires centuries of measurement to do well. The night sky is generous with beauty and stingy with depth. It gives us sparkle immediately. It makes us work for geometry. Consider Orion again, because it is such a useful anchor. Many people can find Orion's belt, 3 stars in a row, and perhaps the faint blur of the Orion Nebula below it. To the eye, this looks like one compact pattern. In reality, Orion contains stars and clouds at different distances, with the nebula itself lying hundreds of light-years away. Behind and around that direction are larger gas structures, young stars and cavities shaped by stellar feedback. When we place Orion into the Radcliffe Wave, we are not saying the constellation drawing is physically real. The hunter shape is a human pattern on the sky. The molecular clouds are physical structures in space. That distinction matters. The sky picture is our story. The three-dimensional map is the galaxy's arrangement. Dust can also create dark lanes that appear dramatic in visible light. Some clouds block background stars so effectively that they look like holes in the sky. But they are not empty holes. They are material in front of brighter background regions. A dark patch may be a dense cloud close enough to hide what lies behind it. In infrared light or radio wavelengths, astronomers can see more of what the dust conceals or trace the gas directly. Different wavelengths act like different senses. Visible light sees starlight and shadows. Infrared light can peer through dust more effectively and detect warm dust emission. Radio observations can trace molecules such as carbon monoxide, often used as a marker for molecular hydrogen that is otherwise hard to observe directly. By combining these tools, astronomers turn darkness into information. That is a lovely reversal, in a very practical way. The thing that hides the Milky Way also reveals it. Dust blocks the view, but the blocking can be measured. Gas is cold and faint, but its molecules leave signatures. Young stars are scattered, but their positions and motions can be tracked. The galaxy does not give up its structure easily, but it leaves clues everywhere, like someone trying to be mysterious while accidentally labeling all the boxes. From inside the Milky Way, the hidden shape was therefore not hidden because it was small. It was hidden because it was too large, too spread out, and too blended with everything else. It crossed broad regions of sky. Its parts had different names. Its depth was uncertain, and our older maps could not quite separate a true three-dimensional filament from a projected ring or a loose collection of clouds. Once the measurements improved, the wave appeared as a coherent feature, and the familiar local clouds gained a new relationship. This changes how we think about our solar neighbourhood. The Sun is currently in a relatively low-density region, known as the local bubble, a cavity of hot, thin gas likely shaped by past supernovae. Around that bubble are denser regions of gas and dust. The Radcliffe Wave lies nearby, forming part of this broader environment of clouds, cavities, and young stars. So the solar system is not floating through a featureless zone. It is moving through an area shaped by previous generations of stars, by explosions, by gas flows, by gravity, and by structures large enough to make our usual sense of neighbourhood feel charmingly inadequate. It is tempting to imagine the Milky Way as a calm city seen from above, with spiral arms like graceful roads and stars like streetlights. But from within, it is messier and more interesting. There are bubbles blown by massive stars. There are shells, filaments, spurs, feathers, and clouds. Some structures form stars. Others are leftovers from star formation. Some are created by shock waves. Others may be stretched by galactic rotation. The Radcliffe Wave belongs to this complicated architecture, and its discovery tells us that even our local arm contains patterns we are still learning to read. The reason this matters is not only that astronomers found a big thing. Big things are common in astronomy. The universe is almost offensively large. What matters is that this big thing is nearby and connected to star formation. It helps explain how local molecular clouds are arranged. It gives astronomers a better framework for studying young stars near the Sun. It challenges older maps. It may provide clues about the forces shaping the gas in our part of the galaxy, and it reminds us that the Milky Way is not a static object. It is a living system in the astronomical sense, constantly reshaped by motion, gravity, birth, and destruction. For a sleepy science journey, that is a satisfying idea to rest with. The familiar night sky above you is not just a pattern of lights. It is the inside view of a galactic landscape. Somewhere beyond the walls of your room, beyond the atmosphere, beyond the quiet turning Earth, the Sun is moving through the disk of the Milky Way. Nearby, long structures of gas and dust stretch across space. Some are making stars. Some are being carved by stars that already formed. Some were known as separate clouds before distance measurements connected them, and one of them, the Radcliffe Wave, has forced astronomers to redraw the local map. So the hidden shape was not invisible because the universe kept it secret in a dramatic way. It was invisible because we had to learn the right kind of seeing. We needed depth, not just direction. We needed dust maps, not just star charts. We needed the patient work of measuring millions of stars, comparing colours, estimating reddening, tracing clouds, and letting computers help reveal what the eye alone could never assemble. The Milky Way had been showing us its pieces all along. We were simply too close to see the pattern. Once astronomers had the tools to turn the flat sky into a three-dimensional neighbourhood, they could begin connecting the clouds themselves. Taurus, Orion, Perseus, Cepheus, and the other familiar regions were no longer just separate names scattered across an atlas of the night. They became markers along a larger structure, and the question shifted from, what are these clouds, to, how did they become part of one enormous wave? The first clue was not a single glowing object in a telescope. It was not a bright spiral, a sudden explosion, or a strange dot that appeared where no dot had been before. It was a pattern hiding inside a collection of things astronomers already knew about. That can be harder to notice than something completely new, because when a thing is familiar, the mind tends to file it away. Orion is over there, Taurus is over there, Perseus is somewhere else, Cepheus has its own clouds. Each region gets its name, its catalogue entries, its papers, its diagrams, and after a while the sky begins to look like a set of labelled drawers. Useful, yes, but sometimes the universe has placed several drawers inside one much larger cabinet, and no one notices until someone finally steps back far enough. Astronomers had studied many nearby star-forming clouds for decades. These clouds are not bright in the ordinary way stars are bright. They are cold regions of gas and dust, often seen as dark patches against the background stars, or traced through infrared and radio observations. They are places where the galaxy stores the raw materials for future stars. Inside them, hydrogen molecules gather in dense pockets. Dust grains help shield the gas from harsh radiation. Gravity slowly finds the places where matter has collected a little more thickly than average. Over time, some of those clumps collapse, warm, spin, flatten, and begin the long process of becoming stars. If stars are the lamps of the galaxy, molecular clouds are some of the workshops where the lamps are assembled, though with far more turbulence and fewer safety signs. For a long time, these nearby clouds were treated mostly as separate neighbourhoods. Taurus was one neighbourhood, Orion was another. Perseus had its own character. Cepheus and others added more pieces to the local star-forming picture. Astronomers knew they were not randomly placed in every direction, and there were older ideas that tried to connect them. The Gould Belt, for instance, was imagined as a ring or belt of young stars and gas tilted relative to the main plane of the Milky Way. It helped explain why many bright young stellar groups seemed arranged in a slanted band around the Sun. For many years, it was a reasonable way to organise the nearby sky. Not perfect, but workable. In science, workable ideas are often the stepping stones to better ones, rather like using a slightly wobbly chair to reach a shelf before finally deciding that perhaps a ladder would have been more sensible. What changed was distance. More exactly, what changed was the quality of distance measurements. A flat sky can fool anyone. If two clouds appear close together from Earth, they may be physically close, or they may simply lie along similar lines of sight at very different distances. If a group of young stars looks like part of a ring, that ring may be real, or it may be a projection effect, a pattern created by placing three-dimensional objects onto a two-dimensional dome. This is the old problem again, the problem of trying to map a galaxy while living inside it. Direction alone gives you a drawing. Distance turns that drawing into a landscape. The Radcliffe Wave began to appear when astronomers used improved three-dimensional dust maps of the solar neighbourhood. These maps relied on stars as background markers. A star has a colour and brightness we can measure. If dust lies between the star and us, the star's light becomes dimmer and redder. The amount of reddening gives clues about how much dust is along that line of sight. But the really useful step comes when you know how far away the star is. If a nearby star shows little reddening, but a farther star in the same direction is strongly reddened, then the dust probably lies somewhere between them. Repeat that not for 10 stars, not for 100, but for millions, and you can begin building a three-dimensional map of dust in space. This method is not as simple as placing little dots on a page. Real stars have different intrinsic colours. Some are naturally redder or bluer. Some are brighter or dimmer because of their age, size, temperature, and chemical composition. Dust itself is uneven. Distances have uncertainties. Lines of sight overlap. The galaxy is messy. If the Milky Way were a neat laboratory experiment, it would probably be rejected for having too many uncontrolled variables. Yet with enough data and careful modelling, the dust begins to reveal its structure. It is a slow kind of detective work, the kind where the footprints are made of missing light. Gaia was one of the major reasons this became possible in a new way. The Gaia spacecraft measured the positions, distances and motions of enormous numbers of stars with remarkable precision. Its work gave astronomers a far better sense of how far away many stars were, especially in the local region of the Milky Way. These distances could then be combined with surveys that measured starlight at different wavelengths. When astronomers brought together parallax measurements, photometry, dust reddening, and statistical models, they could create maps that showed where dust clouds actually sat in three-dimensional space. A useful way to picture this is to imagine a dark room filled with mist and tiny lamps. If you only have a photograph from one side of the room, the mist appears as patches of shadow. You can see where it blocks light, but not how deep it goes. Now imagine that every lamp has a known position, and you can measure exactly how much each one is dimmed. Suddenly the mist becomes a volume. You can tell whether it forms a wall, a clump, a sheet, or a long twisting band. The Milky Way is vastly more complicated than a misty room, and it would not fit comfortably in anyone's house. But the principle is similar. Known background lights make invisible material traceable. Once the local dust was mapped in 3 dimensions, several famous star-forming clouds lined up in a surprising way. They were not arranged as a simple ring around the sun. They formed a long, narrow, wave-like structure. It stretched through the solar neighbourhood over thousands of light years. It rose above and dipped below the plane of the Milky Way. It connected clouds that had often been studied separately. Suddenly, the local map looked different. Taurus, Perseus, Orion, Cepheus, and other regions were no longer just familiar names scattered across the sky. They were markers along a single enormous feature. The discovery was not like finding a new planet, where one object can be pointed to and followed. It was more like realizing that many known islands are actually the peaks of one submerged mountain range. Each island had been real all along. Each had been measured, named, and explored. But the larger connection was hidden beneath the limits of perspective. The Radcliffe Wave was not invisible because it was faint in every possible sense. It was invisible because it was too spread out, too local, and too entangled with the way we had been looking. There is something very human about that. We often understand the world first in pieces. A tree before a forest, a street before a city, a cloud before a weather system. Astronomers do the same because they must. They study one nebula, one cluster, one molecular cloud, one star-forming region. Detailed work matters. Without those close studies, the larger map would have no content. But at certain moments, the pieces begin to rearrange themselves. A new data set arrives. A better method appears. An assumption becomes less comfortable. Then what once looked like separate objects becomes a system. The star-forming clouds themselves are important because they make the Radcliffe Wave more than just a geometric curiosity. This is not a line of random dust. It is associated with stellar nurseries, places where young stars have recently formed or are forming now. The clouds contain dense gas. Young stars nearby provide evidence of recent starbirth. In the Orion region, for example, the Orion Nebula is one of the most famous nearby stellar nurseries, a place where new stars are visible within a glowing cloud of gas. In Taurus, young low-mass stars are scattered through dark molecular material. Perseus contains active star-forming regions as well. These are not dead marks on a map. They're active sites in the life of the galaxy. A molecular cloud's relationship to star formation is slow but direct. The gas begins cold, often only a few tens of degrees above absolute zero. That coldness matters because cooler gas has less thermal pressure resisting collapse. Gravity can gather material more effectively in dense places. Dust helps by shielding molecules from destructive radiation and by allowing gas to cool. Turbulence stirs the cloud, magnetic fields thread through it, and outside events may compress parts of it. Sometimes a shock wave from a nearby supernova or the winds of massive stars can squeeze the gas. Sometimes galactic forces stretch and gather clouds along larger structures. The full story is rarely tidy. Star formation is not like pressing a button. It is more like persuading a large, cold, restless crowd to move in the same direction, which sounds difficult because it is. That's why the Radcliffe Wave matters to astronomers studying how stars form. If many nearby star-forming clouds belong to one large structure, then their histories may be connected. They may have been shaped by the same large-scale forces. They may share a relationship to the motion of gas in the local arm. Their positions might tell us about how the Milky Way organises its raw material. Rather than treating Orion, Taurus and Perseus as isolated local cases, astronomers can ask whether they are beads along a filament, formed or arranged by broader galactic processes. The word wave can be a little misleading if taken too quickly. At the time of the discovery, the name mainly described the shape. The structure looked wave-like in 3 dimensions. It was not yet clear whether it physically moved like a wave. That distinction is important. A winding road has a wave-like shape, but it is not waving at you, unless something has gone very wrong with the road. A rope can lie on the floor in a wavy curve without any motion travelling along it. The first great surprise of the Radcliffe Wave was its shape, a long sinusoidal chain of clouds in the local Milky Way. Later studies would ask whether the clouds and young stars associated with it also had motions consistent with oscillation. But the first step was simply seeing the form. The discovery team used 3-dimensional maps of dust and gas to place the nearby star-forming regions in space. When the clouds were plotted in their true positions, the older ring-like idea weakened. The Gould Belt, as a simple physical ring of nearby clouds around the Sun, did not match the new arrangement well. The Radcliffe Wave gave a better explanation for much of the nearby star-forming material. This is one of those moments where astronomy can feel almost like cartography. The continents have not changed, but the map has been redrawn, and suddenly old routes look different. It is worth pausing on how strange it is that such a large structure could be discovered so recently. The reason is not that previous astronomers were careless. They were working with the tools available to them. Before precise distances, local clouds could not be placed confidently enough in 3 dimensions. Dust clouds on the sky overlap. Young stars are scattered. Gas observations give velocities, but velocity alone does not always translate neatly into distance, especially in the local Milky Way. There were hints and partial models, but not enough clarity. Gaia and modern dust mapping changed the scale of certainty. Even then, the discovery required more than data. It required interpretation. Huge data sets do not automatically explain themselves. They sit there, vast and quiet, like a library where all the books have been poured onto the floor. Astronomers have to decide which relationships matter, which patterns are real, which uncertainties are acceptable, and which older assumptions need to be tested. The Radcliffe Wave emerged from that combination of observation, computation, and careful skepticism. It was not just a pretty picture. It was a claim about physical structure, and claims in science need support. The support came from the coherence of the arrangement. The clouds did not merely happen to appear near each other on the sky. Their 3-dimensional positions traced a connected feature. The structure had a length of thousands of light years and a relatively narrow width compared with its length. It passed within a few hundred light years of the Sun, close in galactic terms. It included many of the major nearby molecular clouds. In shape, it resembled a long ripple, bending above and below the galactic plane. That combination made it difficult to dismiss as a coincidence. Still, one should not imagine the Radcliffe Wave as a solid object with sharp borders. It is not a wall, tube or ribbon you could touch. It is a structure defined by the distribution of gas and dust. Its clouds are separate, lumpy, irregular regions embedded in a larger arrangement. The wave is the pattern connecting them, not a smooth material surface. If you could travel through it, you would not see a glowing line in space like a road painted through the galaxy. Most of it would be very thin by Earth standards, even where it is dense for interstellar space. You might pass through regions where dust slowly reddens starlight, where cold molecules drift, where young stars shine nearby, and where gravity is quietly gathering future suns. The structure is real, but it is not solid. The galaxy builds with fog, not bricks. That idea can be strangely calming. The Milky Way is organized but not rigid. It has shapes made of loose material, moving material that can collapse into stars or be blown apart by stars. The Radcliffe Wave is a structure, but a soft one. It is a cloud architecture. It has enough coherence to map, enough density to form stars, and enough mystery to keep astronomers busy, which is generally what astronomers prefer, though they may pretend otherwise while asking for more telescope time. The discovery also depended on recognizing that star formation is not spread evenly through the galaxy. It often happens in clustered and filamentary structures. Gas tends to collect along lanes, arms, shells, and clouds. The Milky Way's spiral arms are not simply bright decorations. They are regions where gas can be compressed and organized. On smaller scales, turbulence and gravity create filaments within molecular clouds. On larger scales, stellar feedback can blow bubbles and sweep gas into shells. Between those scales, structures like the Radcliffe Wave may tell us how local star-forming material has been shaped by the combined effects of galactic rotation, gravity, and past energetic events. This is one of the reasons the Radcliffe Wave feels like a bridge between the familiar and the enormous. Orion is familiar. Many people have seen it from a garden, a balcony, a pavement, or a car window. The Milky Way's spiral structure is enormous and harder to feel personally. The Radcliffe Wave connects those scales. It says that the famous stellar nurseries near us are part of a galactic scale pattern, not just isolated pretty patches. The small blur below Orion's belt belongs to a wider geography. The local sky has a backbone, or at least a long wavy arrangement that behaves rather like one. The name itself also tells a story about how modern discovery happens. The Radcliffe Wave was named in connection with the Radcliffe Institute where the work was developed, but the discovery drew on global tools and shared datasets. Gaia was launched by the European Space Agency. Ground-based surveys contributed photometry. Dust maps depended on methods developed by teams working across institutions. Modern astronomy is often collaborative in this way. A discovery can involve a spacecraft measuring stars, large surveys collecting light, computers modelling dust, scientists comparing clouds, and someone eventually making a plot that causes several people to lean closer to the screen and say, in more professional language, hang on a moment. That hang on moment is one of the best parts of science. Not because it solves everything, but because it opens the next question. Once the wave was identified, astronomers could ask how it formed. Was it related to spiral arm dynamics? Was it shaped by stellar feedback? Did supernovae help carve nearby cavities and rearrange gas? Was it connected to the local bubble, the low-density region around the Sun? Does it oscillate through the galactic plane? How long has it kept its shape? Is it a temporary feature stretched by galactic shear, or part of a more persistent pattern? A discovery rarely closes a story. More often, it turns on the lights in a room full of additional doors. For us, resting here with the idea, the important point is simpler. Astronomers found the Radcliffe Wave by learning to map nearby dust and gas in 3 dimensions. They took clouds that looked separate on the sky and placed them at their actual distances. They used starlight, reddening, parallax, and careful modelling. The result was a new view of the local Milky Way, a long wave-shaped chain of star-forming clouds, close to the Sun, connecting familiar stellar nurseries into one larger structure. That is a gentle correction to the way we often imagine space. We tend to picture the solar system as surrounded by emptiness, with stars sprinkled far away like decorations on a dark wall. But the space around us has texture. There are cavities, streams, clouds, and regions where new stars are forming. Our solar system is moving through a neighbourhood shaped by older stars and future stars. The Radcliffe Wave is part of that neighbourhood, not in the sense that it is looming over us, but in the sense that it belongs to the same local galactic landscape. Picture again the astronomers building the map. Millions of stars become distance markers. Dust dims some of them and leaves others clearer. Molecular gas appears in radio surveys. Cloud distances are refined. The old tilted ring begins to look less convincing. A long curve emerges. The curve rises and falls. The familiar names settle into place along it. Orion is no longer just a winter constellation with a bright nursery. Taurus is not only a dark cloud region. Perseus is not just another local complex. Together, they help draw the outline of a wave. There is no need to rush past that realization. It is enough for a moment to let the scale sit quietly in the mind. A wave made of star-forming clouds, a nearby structure thousands of light years long, a feature so large that humans saw pieces of it in the sky for generations, without knowing they were connected. Not because the pieces were unimportant, but because the connection required a new kind of map. And once a wave has been found in shape, the next natural question is what kind of wave it really is. Is it merely a curve in the arrangement of gas, like a bent path through the galaxy, or is it a ripple with motion, history, and a cause? What made the Radcliffe Wave so surprising was not only that it was large, or nearby, or full of star-forming material, it was the shape. Once the clouds were placed correctly in 3 dimensions, the local galaxy did not look like a neat little ring around the sun. It looked as if a long band of gas and dust had been lifted and lowered through the Milky Way's disk, forming a curve that rose on one side, dipped on another, and then rose again, like a ripple frozen into a structure thousands of light years long. Not frozen forever, of course, because nothing in the galaxy is truly still, but frozen enough for astronomers to catch its shape in a map and say, very reasonably, well, that is not what we expected. The map was the key. Without it, the Radcliffe Wave would still be disguised as scattered star-forming clouds. We would still look at the sky and see Orion in one direction, Taurus in another, Perseus elsewhere, and Cepheus farther along, each with its own local identity. That is how human beings often make sense of the sky. We divide it. We name it. We draw borders around constellations and regions because otherwise the universe becomes a little too much like opening a cupboard and finding all the cereal poured into one enormous bowl. Names help, boundaries help, but the galaxy itself does not always respect our labels. It connects things across distances that our eyes cannot measure. From Earth, the Radcliffe Wave does not appear as a single glowing arc across the night. That is important. If you went outside tonight and looked up, even under perfect dark skies, you would not see a clean wave drawn through the constellations like a pale ribbon. You might see the Milky Way itself as a soft band. You might find Orion if it is the right season. You might know where Taurus sits, or trace the rough area where Perseus rises, but the wave is not obvious to the eye because the eye sees the sky projected flat. It receives light from every distance at once and places it on a dome. A star a few hundred light years away and a cloud much farther beyond can sit along nearly the same line of sight. They appear close together, but that closeness may be only an accident of perspective. This is why the Radcliffe Wave is really a triumph of mapping. Not mapping in the old sense of drawing where things look as if they are, but mapping in depth. Astronomers had to ask not only, where is this cloud on the sky, but also, how far away is it? How far does it extend? Is it in front of that other cloud, behind it, or part of the same structure? These are difficult questions because dust does not come with a tidy address label. It does not send a postcard saying, "Greetings from 600 light years away, weather cold, hydrogen plentiful." Astronomers have to infer its position by studying the light of stars behind and around it. A dust map begins with something simple in idea and complicated in practice. Dust affects starlight. When light from a star passes through dust, Some of it is absorbed and scattered. The star can look dimmer. It can also look redder, because shorter blue wavelengths are scattered more efficiently than longer red wavelengths. This is a bit like how sunsets look red when sunlight passes through more of Earth's atmosphere, although interstellar dust and Earth's atmosphere are very different materials. In both cases, the colour of light tells you something about what it passed through. The galaxy leaves fingerprints by taking light away. If you know how far away a star is, and you know how much dust has reddened it, you can begin to locate the dust. One star gives a clue. Many stars give a pattern. Millions of stars give a map. Suppose stars up to one distance look mostly clear, while stars just beyond that distance suddenly appear dimmed and reddened. That suggests dust lies somewhere between those two distance ranges. Repeat this along many lines of sight, and the dust begins to take shape in 3 dimensions. This is not a perfect method. It requires assumptions, corrections, and careful treatment of uncertainty. But with enough data, the hidden material becomes less hidden. Gaia made this kind of work far more powerful. By measuring the positions and tiny parallax shifts of stars, Gaia gave astronomers improved distances across large parts of the Milky Way. Parallax is one of those ideas that feels wonderfully practical once you picture it. Hold a finger in front of your face, close one eye, then open it and close the other. Your finger seems to jump against the background. Nearby stars do the same thing as Earth orbits the Sun. Their positions shift by tiny amounts against more distant stars. The closer the star, the larger the shift. Measuring those shifts lets astronomers calculate distances. The shifts are extremely small, so small that if stars had any sense of privacy, Gaia would be accused of staring very intensely indeed. With better distances, the dusty solar neighbourhood could be reconstructed more accurately. And as the maps improved, a long structure appeared. It was not centred on the Sun in the old ring-like way. It stretched across the local region like a great filament. It was narrow compared with its length. It linked major molecular clouds, and instead of lying flat in the Milky Way's midplane, it rose and fell. That rise and fall is what made people describe it as wave-like. The Radcliffe Wave is a ripple not because it is made of water, and not because it is something you could watch crest and break, but because its 3-dimensional shape resembles an undulation in the galaxy's gas. A ripple is a useful image, but we have to handle it gently. In ordinary life, when you hear the word ripple, you might picture a pond after a stone has been dropped into it. Circular waves move outward. The water surface rises and falls. The pattern spreads. But the Radcliffe Wave is not a circular pond ripple, and there is no simple little stone sitting nearby with an embarrassed expression. The Milky Way is a disk of stars, gas and dust, rotating around its centre. The wave is a long chain of clouds within that disk. It bends vertically above and below the galactic plane. Its ripple is a shape in the distribution of matter, not a splash on a surface. Even so, the word fits because the structure has an up and down form. Imagine drawing a line along the dense clouds that make up the wave. Now imagine viewing that line from the side, relative to the flat midplane of the galaxy. Instead of staying level, it curves. It climbs, crosses, descends, and rises again. The pattern is not perfectly smooth, because molecular clouds are not beads on a string placed there by a patient cosmic jeweller. They are irregular and turbulent, but the overall arrangement is coherent enough to stand out. It is not just random scatter. It is a long, organised feature. This is where a map becomes more than a picture. A map can reveal relationships that are too large or too subtle for direct vision. Think about contour lines on a mountain map. If you stand in one valley, you see slopes and trees. You may not realise the whole region forms a long ridge, but when the land is mapped from above and side elevations are included, the shape becomes obvious. The Radcliffe Wave was similar. We were standing inside the galactic landscape, seeing individual valleys and slopes. The 3-dimensional map gave the side view. Suddenly the ridge was there. The old Gould belt idea made sense from the earlier view because many nearby young stars and gas clouds seemed to form a tilted band around us. It looked as if the sun sat near the centre of a slanted ring of star formation. That picture had a certain neatness, and neatness is attractive. The universe, however, is not required to be neat just because it would make better wall art. When the three-dimensional positions were improved, much of that ring-like arrangement dissolved into a different geometry. The local star-forming regions were better explained as part of a filamentary wave, not a belt wrapped around the sun. The sun was not at the centre of a tidy local ring. It was near a much larger structure passing through the neighbourhood. That change matters because it alters the story we tell about local star formation. A ring suggests expansion from a central event or a circular local arrangement. A wave suggests something stretched, coherent, and possibly shaped by larger galactic forces. It points attention away from a sun-centered picture and toward the dynamics of the Milky Way's gas. The clouds are not simply around us, they are part of their own structure. We happen to be close enough to study them in detail, which is convenient for us, though probably not something the clouds arrange deliberately. The actual scale is difficult to hold in the mind. The Radcliffe Wave is thousands of light years long. Light itself would need thousands of years to travel from one end to the other. Human history, with all its cities, languages, mistakes, improvements, and suspiciously persistent paperwork, fits into a tiny sliver of that travel time. Yet in the Milky Way, a structure thousands of light years long is local. That is one of astronomy's little tricks. It takes words like nearby and stretches them until they no longer behave the way they do in everyday life. Nearby, in this case, can mean hundreds of light years away. A neighbourhood can be larger than all human civilization's history in light travel distance. Astronomy is not rude about this. It simply has very large furniture. The wave's vertical motion through the galactic plane, or at least its vertical shape, also tells us something important about the Milky Way disk. The galaxy is often drawn as flat, but flat does not mean perfectly thin or perfectly still. The disk has thickness. Stars and gas can move above and below its mid-plane. Gravity pulls material back toward the centre of the disk, but disturbances can lift and bend gas. A passing object, a spiral arm interaction, a supernova-driven bubble, or other galactic processes may push, compress or rearrange clouds. The Radcliffe Wave shows that the nearby gas layer has structure in the vertical direction. It is not simply spread out like a smooth pancake, though now that image is in the room, we may as well admit that the Milky Way is much harder to flip. When astronomers plotted the wave, they were seeing the local molecular clouds as part of a larger filament. Molecular clouds are especially important because they are tied to star formation. The densest parts can collapse into new stars. This means the Radcliffe Wave is not merely a passive feature. It contains places where the next generation of stars is being made. The Orion complex, Taurus, Perseus and other regions are not decorations along the wave, they are active sites within it. The ripple is made of material that participates in the galaxy's renewal. There is something quietly satisfying about a ripple made of stellar nurseries. On Earth, a ripple on water is temporary. It spreads and fades. In the galaxy, a ripple in gas can hold clouds massive enough to form stars, and those stars can live for millions or billions of years. Some may eventually explode, enriching nearby space with heavier elements. Others may live calmly for ages. Around some, disks of dust may form planets. The Radcliffe Wave is not just a shape, it is part of a chain of events. Gas becomes stars, stars shape gas. The map shows structure, but the structure is also a process. A major reason the wave looks coherent is that its clouds align over a large distance, while staying relatively close to a thin path. They do not form a random ball around the sun, they trace a band. That band undulates. The word sinusoidal is often used in scientific descriptions, meaning it resembles the smooth up and down curve of a sine wave. For narration, we can simply say it rises and falls in a regular-looking way, though not perfectly. Nature rarely draws with a ruler. It prefers a slightly messy hand, especially when turbulence, gravity, magnetic fields, and stellar feedback are all invited to the same meeting. The map also revealed that the wave passes fairly close to the Sun in galactic terms. This closeness makes it especially valuable. Nearby structures can be studied with more detail than distant ones. Individual young stars can be measured. Dust can be mapped more accurately. Gas velocities can be compared. If the Radcliffe Wave were far across the galaxy, it might still be interesting, but it would be harder to study. Instead, it sits in our broader neighbourhood like a long laboratory of star formation and galactic structure. We do not need to travel to it, which is fortunate because packing for a journey of several hundred light years would be challenging, and someone would still forget the charger. The fact that the wave had remained hidden also says something about how science changes with tools. People did not miss it because they were not looking at the sky. They missed it because the needed depth information was not available in the right form. A two-dimensional view can hide a three-dimensional structure. That is true in astronomy, medicine, geology, and even ordinary life. A pile of papers on a desk can look random until you realize it is actually arranged by someone else's mysterious personal logic, which is perhaps the most difficult mapping problem of all. In the Milky Way, the papers were molecular clouds, and the missing organization was depth. Once the wave was found, it offered a new way to connect familiar regions. Orion became part of a longer galactic feature. Taurus and Perseus became neighbouring pieces along the same broad arrangement. The map turned a collection of local clouds into a single structure with a name. This naming is not just cosmetic. Names help scientists discuss patterns, compare models, and ask shared questions. Before the name, there were many regions. After the name, there was a feature to investigate. Still, the name should not make us think the borders are sharp. The Radcliffe Wave is not like a country on a political map where one side of a line belongs to it and the other side does not. Interstellar structures are fuzzy. Gas fades gradually. Clouds overlap. Some regions are clearly part of the structure, while others may be related less directly. Astronomers define the wave based on the best available data and the coherent arrangement of major clouds. Future maps may refine its shape, extend it, complicate it, or reveal nearby structures with similar forms. This is not a weakness. It is how maps improve. The first good map of a coastline is not the final word on every inlet. The phrase cosmic ripple also invites a question. If it looks like a ripple, what made it? That is not fully settled. Several possibilities have been discussed. The wave could be related to the dynamics of the Milky Way's spiral structure. It could have been shaped by stellar feedback, such as explosions and winds from previous generations of massive stars. It could involve gravitational disturbances, perhaps from interactions that caused gas in the disk to oscillate. It may connect in some way with the local bubble, the large cavity of hot, thin gas surrounding the Sun, which was likely carved by ancient supernovae. At this point in the story, we do not need to choose one answer too quickly. The important step is seeing that the shape exists. Causes come after the map. That order matters. First, identify the structure, then measure it more carefully, then study its motion, then test possible origins. Science does not always move in a straight line, but it often benefits from that kind of patience. If we leap too quickly to the cause, we may explain the wrong thing. The Radcliffe Wave's shape had to be established before astronomers could ask whether it is physically oscillating, whether it has a particular age, or whether it was created by a known event. The map gave the question a body. It turned speculation into something measurable. What is especially pleasant in a calm, late-night way is that the map revealed the wave not by making the universe louder, but by making our view more careful. No explosion announced it. No dramatic flash crossed the sky. No ancient warning arrived carved into a comet, which is probably for the best because comets have enough to do. The discovery came from precision. from distances, from reddening, from dust, from putting clouds in their correct places. It is a quiet kind of revelation, suited very well to a sleepy science story. The galaxy did not shout. It waited for the map to become good enough. If you imagine the Milky Way from above, the Radcliffe Wave would not dominate the entire galaxy. It is large by human standards, but local by galactic standards. It is a feature in our part of the disk connected with the local arm or Orion Arm region, but from our perspective it is enormous. It rearranges the local stellar nurseries into a long chain. It gives shape to the gas around us. It suggests that our neighbourhood is not merely a random patch between spiral arms, but a region with real architecture. Now picture the map itself, not as a technical plot, but as a kind of slow unfolding. At first, there is the sun, a reference point near the centre of the local view. Around it are known clouds, each at its measured distance. The points and volumes begin to assemble. Orion falls into place, Taurus falls into place, Perseus and Cepheus and other regions settle into depth. The old ring begins to loosen. A long filament appears. It bends, it rises, it dips, it resembles a wave. Suddenly the familiar sky has a hidden profile. That profile is what the eye could not see. We can see brightness, we can see patterns, we can see the Milky Way as a pale band. But we cannot directly see depth in the night sky across hundreds or thousands of light years. Our two eyes are separated by only a few centimetres, wonderful for finding a cup on a table, less useful for judging the distance to a nebula in Orion. For cosmic depth, we needed a spacecraft measuring parallax, surveys measuring colours and brightness, and models turning all of it into a three-dimensional reconstruction. The human eye opened the story. Instruments gave it depth. And once depth arrived, the ripple became a real part of our map of home. The Radcliffe Wave is not a mythic curve drawn for beauty. It is an arrangement of gas and dust in space. It is a connection between clouds. It is a structure near the sun. It is a reminder that the Milky Way, even close by, has shapes that were waiting for the right viewpoint. We did not need to leave the galaxy to see them. We needed to measure the galaxy from within more carefully. So when we ask why the Radcliffe Wave looks like a cosmic ripple, the first answer is that its material is distributed in a long, undulating form. The second answer is that our old view flattened that form into confusion. And the third answer is that modern maps gave astronomers the depth needed to recognise the ripple as one connected structure. It looks like a ripple because the clouds themselves rise and fall through the galactic plane. It became visible because the map stopped treating the sky as only a surface. Along the Radcliffe Wave, the most important things are not bright stars already shining in their long, steady adulthood. They are the cold places before the stars, the shadowed places, the thick clouds where gravity still has work to do. These are stellar nurseries, although that phrase can make them sound a little gentler than they are. A nursery on Earth might have blankets, soft lights, and someone whispering because a baby has finally fallen asleep. A stellar nursery is a cold molecular cloud with turbulent gas, magnetic fields, radiation jets, collapsing clumps and young stars throwing material into space like toddlers who have discovered porridge. Still, the name fits in one important way. These are the places where stars begin. The Radcliffe Wave matters because it is not just a curve of empty space. It is a chain of clouds that includes many of the nearby regions where stars are being born or have recently been born. If the wave were only a line on a map, it would be interesting as geometry. But because it carries star-forming material, it becomes part of the Milky Way's life cycle. Gas gathers, dense pockets form, stars ignite, new young clusters drift away from their birth clouds. Massive stars shine, push, and eventually explode, shaping the next generation of clouds. The wave is not just a shape, it is a route along which the galaxy is making fresh suns. To understand why these places ride along the wave, we need to begin with the material itself. Most of the ordinary matter between stars in a galaxy is gas, with some dust mixed in. The gas is mostly hydrogen, because hydrogen is the simplest and most common element in the universe. In many regions of space, hydrogen is spread so thinly that it is hard to imagine calling it matter at all. Even the denser parts of interstellar space would count as an excellent vacuum by Earth standards. But in molecular clouds, the gas becomes dense enough and cold enough for hydrogen atoms to pair into hydrogen molecules. These clouds are dark, cold, and irregular. They do not look like the bright, cheerful clouds you might see outside a window. They are more like enormous, slow, cold fog banks drifting through the galaxy, except each one may contain enough material to make thousands or even millions of stars. Dust grains are mixed into these clouds, and those grains are surprisingly important. They help shield molecules from harsh ultraviolet light. They allow gas to cool. They provide surfaces where atoms can meet and form molecules. Dust also blocks visible light, which is why many molecular clouds appear as dark patches against the background stars. When you see a dark nebula, you're not looking at emptiness. You're looking at material thick enough to hide the light behind it. It is the galaxy closing a curtain over a room where something is being assembled. Inside these clouds, star formation begins when parts of the gas become dense enough for gravity to take over. A clump of gas may be squeezed by turbulence, by the pressure from nearby stars, by shock waves, or by the slow gathering of material along filaments. Once gravity wins locally, the clump collapses. As it collapses, it heats up. It spins. It often forms a disk. Material falls toward the center, and a young protostar begins to grow. Some of the material is not swallowed quietly. It can be blasted outward in jets, narrow streams that shoot from the poles of the young object. So even at the beginning, a star is not exactly peaceful. It is more like a very small cosmic engine starting in a cold garage. The Radcliffe Wave contains several famous cloud complexes where this process is happening or has happened recently. One of the best known is the Orion region. Orion is familiar because its bright stars make a recognizable pattern in the night sky, but the constellation is only the surface of the story. Behind that familiar shape lies the Orion Molecular Cloud Complex, one of the nearest major star-forming regions to Earth. The Orion Nebula, visible as a faint fuzzy patch below Orion's belt under decent skies, is a glowing portion of this larger complex. It is lit by young, hot stars that have already formed within it. In telescopes and images, the Orion Nebula looks dramatic with folds of gas, bright knots, dark lanes, and newborn stars still surrounded by their birth material. It is one of the places where we can watch star formation almost next door, at least by galactic standards. Orion is not alone. Taurus is another important region along the broader structure. The Taurus molecular cloud is darker and quieter looking than Orion. It does not have the same spectacular bright nebula visible to the eye, but it is rich in young low-mass stars. Taurus is especially useful for studying how stars like the Sun may form, because it contains many young stars that are not as massive or disruptive as the hot stars in Orion. Some are surrounded by disks of gas and dust, the kind of disks that can eventually give rise to planets. In Taurus, astronomers can study early stellar growth in a somewhat calmer environment. Calm, of course, is relative. A young star with jets and a disk is not exactly a sleeping kitten, but compared with the fierce radiation of Orion's massive stars, Taurus can seem almost polite. Perseus adds another piece to the chain. The Perseus molecular cloud contains active star-forming regions such as NGC 1333 and IC 348, where young stars and protostars are embedded in gas and dust. These regions allow astronomers to study different stages of stellar birth, from dense cores before collapse to young clusters where stars have already emerged. Perseus is particularly interesting because it shows how varied star formation can be even within one cloud complex. Some areas are crowded and active, others are quieter. The cloud is not a factory with identical assembly lines. It is more like a landscape with different weather in every valley. Farther along the wave, Cepheus and other regions continue the story. Cepheus contains associations of young stars and cloud material connected to the broader pattern. Other major regions linked with the wave include the North America Nebula area and Cygnus X, both associated with active star formation farther from the Sun. Cygnus X, in particular, is a massive and complex region where many young hot stars shape the surrounding gas. The North America Nebula gets its name because, in images, its bright gas resembles the outline of the continent, which is a very human thing to do, seeing geography in glowing hydrogen. The nebula itself, however, is not concerned with cartography. It is part of a larger star-forming environment in the Milky Way, and in the Radcliffe Wave picture, it becomes one of the distant landmarks along the structure. This is where the wave begins to feel less like a single object and more like a road lined with nurseries. Not nurseries placed at even intervals, and not a road with smooth pavement, but a long galactic structure where cold material has gathered in many significant regions. Some parts are active now, some have already produced young clusters, some may be forming stars more slowly. The arrangement suggests that nearby star formation is not simply a set of unrelated local events. It may be tied to the way gas is organised on larger scales. Young stars are useful tracers because they have not had much time to wander far from their birthplaces. An old star can travel around the galaxy for billions of years, mixing with many populations and losing any obvious connection to the cloud where it was born. The Sun itself is about 4.6 billion years old and has orbited the Milky Way many times. It no longer sits beside its birth cloud, and that cloud is almost certainly gone or transformed beyond recognition. Young stars, by contrast, are still near home. If you find a group of young stars near a molecular cloud, there is a good chance they formed there or nearby. They are like footprints still fresh in soft ground. This is why astronomers study young clusters and associations along the Radcliffe Wave. The gas shows where star-forming material is now. The young stars show where star formation has recently occurred. Together they help reveal the history of the wave. If clusters and gas both follow the same broad structure, that strengthens the idea that the wave is not just a coincidental arrangement of clouds. It becomes a connected system, one that has been forming stars along its length. But the relationship between gas and stars is not always simple. Once a star forms, especially a massive one, it begins to affect its surroundings. Hot young stars flood nearby gas with ultraviolet radiation. They can ionize hydrogen, making it glow. Stellar winds push material outward. Supernova explosions from massive stars can carve bubbles and shells into the interstellar medium. These processes can destroy parts of a molecular cloud, but they can also compress nearby gas and trigger new star formation. The galaxy has a habit of turning endings into beginnings. A massive star may blow away the cloud that made it, while also squeezing another cloud into collapse. It is untidy, dramatic, and very efficient at keeping astronomers awake. Along the Radcliffe Wave, these feedback processes may have helped shape some of the visible structures. The local neighbourhood contains cavities and bubbles, including the local bubble around the Sun. This bubble is a region of hot, thin gas thought to have been carved by supernovae over the past several million years. Around such bubbles, denser gas can be swept into shells where star formation may occur. The Radcliffe Wave and nearby bubble structures are part of the same broad environment, and astronomers are still working out exactly how they relate. The details are not fully settled, but the general picture is clear enough to be fascinating. Our solar system sits near a region where old stellar explosions, cold clouds, and young stars have all helped sculpt the local Milky Way. There is a practical reason to study these nurseries together. If each cloud is treated separately, astronomers can learn a great deal about local star formation. But if those clouds are part of one long wave, then their shared arrangement may reveal a larger cause. Perhaps the gas was lifted and compressed by a disturbance in the galactic disk. Perhaps spiral arm dynamics helped organize the material. Perhaps feedback from earlier generations of massive stars helped carve and gather the clouds. Perhaps several effects work together, because the universe rarely chooses the simplest paperwork option. By studying the nurseries along the wave, scientists can look for patterns in age, motion, position, and chemistry that point to a shared history. Chemistry matters because stars inherit the composition of the gas clouds from which they form. If young clusters along the wave share certain chemical similarities, that can suggest something about the mixing and history of their birth material. If they differ, that too is useful. The Milky Way's gas is not perfectly mixed. Different regions may contain slightly different amounts of heavier elements, depending on past generations of stars and supernovae. Studying young stars along the Radcliffe Wave is therefore a bit like sampling water from different points along a long river. The samples can tell you whether the river has a common source, where tributaries entered, and how the material changed along the way. In this case, the river is made of gas and young stars, which makes the glassware more complicated. The nurseries along the wave also show that star formation is not evenly spread. Even within a giant molecular structure, stars form in clusters and knots. Dense filaments inside clouds feed material into cores. Some cores collapse, others do not. Some regions produce massive stars that reshape everything around them. Others produce mostly smaller stars that evolve more quietly. So the Radcliffe Wave is not a continuous string of newborn suns. It is a long structure with pockets of activity. Some beads glow brightly, some are dark, some are still gathering themselves. This unevenness is normal. Gravity needs density to work efficiently. A molecular cloud may contain a lot of gas overall, but only a fraction of it may be dense enough at any given time to form stars. Turbulence can both help and hinder the process. It can compress gas into dense clumps, but it can also stir the cloud and keep much of it from collapsing all at once. Magnetic fields add another layer of support and complexity. Radiation from nearby stars can heat or disperse material. Star formation is therefore selective. The galaxy does not turn every available bit of gas into stars immediately. It proceeds in patches, in waves of activity, in slow local decisions made by physics. One of the helpful things about nearby stellar nurseries is that they let astronomers study star formation across different environments. Orion, with its massive young stars, shows what happens when intense radiation and crowded conditions dominate. Taurus, quieter and rich in low-mass young stars, offers another version of the story. Perseus gives still another mix of embedded protostars and young clusters. Cygnus X, more distant and massive, shows large-scale energetic star formation. When these regions are viewed along the Radcliffe Wave, they become examples along a connected structure. The variety is not a distraction, it is the point. A single wave can host many kinds of stellar birth. For a listener lying comfortably in the dark, this may be the nicest way to picture the Radcliffe Wave. Not as a threat, not as a wall, not as a mysterious force looming around the solar system. Instead, imagine a long, cold, uneven chain of clouds stretching through our local part of the Milky Way. Along it, here and there, gas has thickened enough for gravity to begin. Some places are still dark. Some glow because young stars have lit them from within. Some have already made clusters that are slowly drifting away. The wave is less like an ocean wave coming toward us, and more like a galactic hedgerow, with small bright nests of stars tucked into it. The word riding is useful, but again we should treat it carefully. The stellar nurseries are not sitting on top of the wave the way boats sit on water. They are part of the wave. The clouds define the structure. The young stars mark where parts of it have recently collapsed into light. The gas and stars move through the galaxy under the influence of gravity, rotation, and local forces. Everything is in motion, but the timescales are so long that the movement is not something human senses can directly watch. A cloud may change over millions of years. A young cluster may disperse over tens or hundreds of millions. The whole wave may oscillate through the galactic plane on timescales far longer than human civilization. It is motion in a very slow language, and yet even slow motion matters. If the wave is oscillating, as later studies suggest, then these stellar nurseries are not just arranged along a wavy shape. They may be participating in a larger movement through the Milky Way's disk. Their positions and motions become clues. The gas has velocities. Young clusters have three-dimensional motions measured through a combination of proper motion, distance, and sometimes radial velocity. Astronomers can compare where the clouds are with how they move. This is how a map becomes a movie, although a movie that plays so slowly it would make even the most patient director ask for a chair. Before we move fully into that motion, it helps to hold on to the material nature of the wave. A wave of star-forming clouds is not an empty mathematical line. It contains cold gas, dust, young stars, and nebulae. It includes regions people have looked at for generations without knowing they were connected. When someone photographs Orion, they are not just capturing a beautiful nebula. They are looking at one bright piece of a much larger local structure. When astronomers study Taurus, they are studying another quieter part of the same broader arrangement. When young clusters in Cepheus or Cygnus are measured, they help trace the far reaches of the wave. This gives the night sky a new kind of depth. The constellations remain useful for finding your way. Orion is still Orion to our eyes, Taurus is still Taurus, Cygnus still spreads like a swan across the summer sky. But underneath those human patterns lies a physical geography that does not match the constellation borders. The Radcliffe Wave crosses through the real three-dimensional galaxy, not the old drawings we placed on the sky. It reminds us that the stars we group together by sight may be unrelated, while clouds in different constellations may be part of one physical structure. The sky is both a storybook and a map, and sometimes the map has been folded in a way we are only just learning to unfold. The young stars along the wave also place our own solar system in a wider family history. The Sun is not part of the Radcliffe Wave's current star formation. It is much older, and it formed elsewhere from another cloud long gone. But the same processes that made the Sun are happening now along this nearby structure. Cold gas is collapsing, disks are forming, planets may eventually assemble around some of those young stars. The ingredients that once made our own system are being rearranged nearby into new systems. Somewhere along the wave, small dusty disks may be forming worlds that will not cool into stability for millions of years. Perhaps some will become rocky planets. Perhaps some will become gas giants. Most will simply follow the ordinary messy outcomes of planet formation, which is already extraordinary enough. There is comfort in that continuity. The Radcliffe Wave is not only a scientific discovery, it is a reminder that our solar system came from the same galactic habits still at work around us. Stars do not appear from nowhere. They condense from clouds. Clouds are shaped by previous stars. Those stars return material to space. The galaxy reuses itself. It is not a single event, but a long recycling process with gravity, radiation, gas, dust, and time all taking turns. The wave carries part of that process through our neighbourhood. So when we speak of stellar nurseries riding along the Radcliffe Wave, we are really speaking about the Milky Way's nearby machinery of renewal. Orion, Taurus, Perseus, Cepheus, the North America Nebula region, Cygnus X, and other related complexes are not random scenic stops. They are places where cold material becomes luminous. They are evidence that the wave is physically meaningful. They are the bright and dark markers that let astronomers trace the structure's length, study its history, and ask how it moves. The strange thing about the Radcliffe Wave is that once astronomers saw its shape, the next question almost asked itself. A wave-shaped structure is one thing. A structure that actually moves like a wave is something else entirely. A winding road can look like a wave from above, but nobody expects the road to rise and fall under the cars unless something has gone deeply wrong with local engineering. A ribbon can be laid on a table in a wavy curve and remain perfectly still. So when astronomers first mapped this long chain of star-forming clouds, the word wave described its form. It was a shape in space, a huge undulating arrangement of gas and dust near the sun. But then came the more difficult question. Is the Radcliffe Wave only shaped like a ripple, or is the material itself moving in a ripple-like way? That question sounds simple until you remember the scale. We cannot sit beside the Radcliffe Wave and watch it sway. We cannot set up a camera and record a few afternoons of galactic motion. The entire structure is thousands of light years long, and the timescales involved are measured in millions of years. If the wave is moving, it is moving slowly by human standards, even though its actual speeds through space are significant. This is one of astronomy's usual tricks. The motions are enormous, but the distances are so much more enormous that everything appears still. Stars move, gas flows, clouds drift. The sun itself races around the Milky Way. Yet from a human lifetime, the night sky looks calm enough to hang dreams on. To find motion in something like the Radcliffe Wave, astronomers need measurements, not eyesight. They need to know where the clouds are, how far away they are, and how their gas and young stars are moving. The three-dimensional map gave the structure its shape. Then the kinematic data, which is just a calm, scientific way of saying motion data, began to reveal whether the shape had behaviour. If the clouds were simply arranged in a wavy line but moving randomly, then the wave would be a geometric pattern only. But if different parts of the structure moved in a coordinated way, rising and falling through the Milky Way's disk, then the wave would be more than a shape. It would be a motion written into the gas. Astronomers approached this problem by using two kinds of tracers. One was the gas itself, especially molecular gas observed through radio emission. The other was young stars and young stellar clusters associated with the same cloud complexes. The gas is the material of the wave. The young stars are useful because they were born from that gas recently enough that their motions still preserve clues about the material they came from. An old star may have wandered far from its birthplace over hundreds of millions or billions of years. A young cluster is more like a fresh footprint. It has not yet walked far from the soft ground where it formed. Gas motion can be measured in part through the Doppler effect. When gas emits light at a known wavelength, and that wavelength is shifted slightly because the gas is moving toward or away from us, astronomers can measure its line-of-sight velocity. This is the same basic idea behind the change in pitch you hear when an ambulance passes by, except in space we are listening with light and radio waves rather than ears, and the ambulance is a cold molecular cloud, which is admittedly less urgent but far larger. Molecular gas often contains carbon monoxide, or CO, which is useful because molecular hydrogen, the main ingredient, is difficult to observe directly in cold clouds. CO acts as a tracer, leaving spectral signatures that help astronomers follow the movement of molecular material. Young stars add another layer. Gaia can measure their positions, distances, and proper motions, which means their movement across the sky. When radial velocities are also available, astronomers can reconstruct three-dimensional motion. Proper motion is tiny. A star may move a great distance over thousands of years, but from Earth its position shifts only slightly against the background. Gaia measures these tiny shifts with extraordinary precision, turning what appears fixed into something alive with motion. It is rather like discovering that the still photograph on your wall is actually a very slow video. When researchers combined these measurements, they found evidence that the Radcliffe Wave does not merely look like a wave. It appears to be oscillating through the plane of the Milky Way. That means different parts of it are moving up and down relative to the galaxy's mid-plane in a coherent pattern. The wave also appears to be drifting outward from the galactic centre, so the structure is not simply lying there as a curved chain of clouds. It is moving through the galaxy as part of the Milky Way's larger gravitational environment. A useful comparison is the wave in a stadium. When people do the wave, each person mostly moves up and down in place. The pattern travels around the stadium even though the people do not run around the seats. One section stands, then sits. The next section stands, then sits. The motion of individuals creates a travelling pattern. The Radcliffe Wave is not exactly the same, because gas clouds and young stars are not enthusiastic sports fans, and the Milky Way does not sell overpriced snacks at the aisle. But the image helps. The structure can move in a coordinated way even if the material is not all rushing in one simple direction. Different parts rise and fall through the galactic disk, creating a wave-like motion across a huge region of space. This does not mean the Radcliffe Wave is flapping wildly. It is not wobbling like a loose bedsheet in a storm. Galactic motion is slow, controlled by gravity, rotation, and the mass distribution of the Milky Way. The wave's movement is measured across enormous timescales. If you could watch it from far outside the galaxy, speeding up millions of years into seconds, you might see the structure gently oscillate around the midplane, rising and falling as the galaxy's gravity pulls it back. But at normal speed, it would seem almost completely still. The galaxy moves in a language too slow for human senses. The Milky Way's disk has a midplane, a kind of average central layer where much of the gas and many stars are concentrated. But objects do not stay perfectly on that plane. Stars can bob above and below it as they orbit the galaxy. Gas can be lifted, compressed, and disturbed. Gravity acts like a restoring influence, pulling material back toward the denser central region of the disk. If something pushes gas upward, the galaxy's gravity can pull it back down. It may overshoot, rise again, and oscillate. This is not identical to a spring, but the idea is similar enough to be helpful. Disturb a system, and gravity tries to restore it. The result can be a slow up and down motion. In the Radcliffe Wave's case, the evidence suggests that the clouds and young stars associated with it may be participating in this vertical oscillation. The most massive star-forming regions along the wave, including places associated with Orion, Cepheus, the North American Nebula region, and Cygnus X, can be studied as markers. Their positions show the shape, their velocities show the motion. Together, those measurements allow astronomers to model the wave as a coherent structure moving through the galactic plane. There is a very satisfying logic to this. First, astronomers mapped where the clouds are. Then they asked how the clouds and young stars move. The shape said, "I look like a wave." The motion data answered, "I may be behaving like one too." That does not make the story complete, but it makes it far more interesting. A static curve can tell us about where gas has gathered. A moving wave can tell us about the forces acting on the local Milky Way, because if the Radcliffe Wave is oscillating, then its motion becomes a probe of the galaxy itself. The way it rises and falls depends on the gravitational field of the Milky Way near the Sun. Gravity is shaped by mass, stars, gas, dust, dark matter, and everything else contributing to the local gravitational potential. By studying how the wave moves, astronomers can learn something about that mass distribution. It is rather like watching a buoy bob in water to infer the waves and currents around it. The buoy is not the ocean, but its motion carries information about the ocean. The Radcliffe Wave is not the whole Milky Way, but its oscillation carries clues about the local galactic environment. This is one reason scientists became especially excited by the motion study. The Radcliffe Wave is not only a strange nearby object, it is a tool. Its huge size and coherent structure make it useful for testing how gas responds to the Milky Way's gravity. And because it lies near the Sun, it can help refine our understanding of the local gravitational field, including the Sun's own vertical motion through the disk. The Sun does not orbit the galaxy in a perfectly flat line. It also moves above and below the midplane over time, like a bead on a very large, very slow galactic string. Studying the Radcliffe Wave's motion may help measure aspects of that local vertical rhythm. There is also the outward drift. The evidence suggests that the wave is drifting radially away from the galactic centre. In the Milky Way, radial motion means motion inward or outward relative to the centre of the galaxy. This does not replace the main orbital motion around the galaxy. The wave, the Sun, and nearby stars are all orbiting the galactic centre as part of the disk. But on top of that, structures can have additional motions, including outward or inward drift. The Radcliffe Wave's outward movement adds another piece to the puzzle of how it formed and how it interacts with the rest of the local arm. This drift may connect to one of the most interesting nearby features, the local bubble. Our solar system sits inside this bubble, a large cavity of hot, thin gas surrounded by denser material. It was likely carved by a series of supernova explosions from massive stars over the past several million years. The idea is that massive stars formed, lived short lives, exploded, and cleared out a region around them. The Sun is currently inside that cavity, not because the Sun made it, but because our solar system has moved into or resides within this environment. If the stellar group that produced those supernovae was born in the Radcliffe Wave, then the wave may be linked not only to current star formation, but also to the bubble that surrounds our solar system today. That possibility is still an area of active research, but it is a beautiful example of how local structures connect. A wave of star-forming gas produces massive stars. Massive stars explode. Explosions carve bubbles. Bubbles reshape surrounding gas. New stars may form along the edges. The Sun moves through the resulting landscape. None of these events is isolated. The Milky Way is a chain of causes, but stretched across such huge distances and times that the connections are easy to miss. The Radcliffe Wave gives astronomers a framework for tracing some of those connections in our own neighbourhood. Of course, caution is important. Astronomy is full of structures that look persuasive until better data complicates them. The Radcliffe Wave's oscillation is supported by recent analysis, but scientists will continue testing it. Other researchers may refine the model, challenge assumptions, or show that the motion is more complicated than a single coherent wave. Gas clouds are not rigid bodies. They can shear because the Milky Way rotates differentially, meaning material at different distances from the centre orbits at different rates. Clouds can stretch, merge, disperse, and respond to local forces. So when we say the Radcliffe Wave is moving like a wave, we are not saying it is a perfect solid ribbon swinging through space. It is a messy interstellar structure whose overall motion appears wave-like. That distinction keeps the science honest. The wave is real as a mapped structure. Its oscillation is supported by evidence, but the details are still being worked out. It may not move as one perfectly connected object. Parts of it may have different histories. Some clouds may be more tightly associated than others. The material may evolve over tens of millions of years, changing shape as galactic shear and local feedback pull it apart or reshape it. The more astronomers study it, the more nuanced the picture will become. This is not a problem. It is exactly what should happen when science meets a complex galaxy. Still, the basic conclusion is remarkable. A structure near the Sun, made of dense gas and star-forming clouds, appears to be oscillating through the galactic plane. It is not merely a pretty curve in a map. It has motion. It has dynamics. It participates in the larger breathing and bending of the Milky Way's disk. The word breathing is only a metaphor, of course. The galaxy has no lungs, which is probably fortunate given the amount of dust involved. But the disk does move, flex, and respond. It is not a rigid plate. It is a rotating system of stars, gas, dust, and dark matter, always shifting under gravity. This gives us a different way to imagine our home galaxy. The Milky Way is often shown as a flat spiral, a graceful disk with bright arms. That image is useful, but it can make the galaxy seem too still. In reality, the disk is stirred. It has ripples, warps, bending waves, shells, bubbles, and streams. Some of these may be caused by internal processes, such as spiral arms and star formation. Others may be influenced by outside events, such as encounters with smaller galaxies or the gravitational pull of satellites. The Radcliffe Wave is a nearby example of that restlessness. It shows that even our local star-forming environment is part of the galaxy's motion, not just its architecture. The phrase, moving through space, can also be a little misleading if we imagine the wave travelling through empty space like an object thrown across a room. The wave is embedded in the Milky Way. It is part of the disk. Its gas, clouds and young stars orbit the galaxy while also moving vertically and radially. It is less like a ship crossing an ocean and more like a ripple inside the ocean itself. The wave does not move through the Milky Way as an outsider. It is the Milky Way moving in a particular local pattern. For anyone listening in the dark, this may make the solar neighbourhood feel more alive. The Sun is not simply parked in a quiet cosmic suburb. It is orbiting through a dynamic disk. Nearby, a great wave of star-forming material rises and falls. Young stars along it remember the motion of their birth clouds. Gas carries velocity signatures. The local bubble around us may be linked to previous massive stars born in the same broader structure. Our environment is not empty. It has history, motion, and shape. It is also worth remembering that the Radcliffe Wave's movement is not dangerous to us in any immediate sense. It is not crashing over the solar system. It is not a galactic tsunami. Space is too vast and the gas is too thin for that kind of image to be useful. Even dense molecular clouds are extremely diffuse compared with air on Earth. The wave's importance is not that it threatens us, but that it reveals the moving structure of the galaxy around us. It is a discovery about context. It tells us more about the neighbourhood through which the Sun travels, and this is where the emotional scale of astronomy can be quietly strange. On one hand, the motion is too slow to see. On the other, it is happening right now. The clouds are moving, the young stars are moving, the Sun is moving. The Milky Way's disk is not frozen. Every calm night sky is actually a snapshot of a system in motion. The stillness is only a matter of timescale. If we could live for tens of millions of years and keep looking up, the constellations would distort, stellar nurseries would change, clouds would drift, and the Radcliffe Wave would continue its long oscillation through the galactic plane. The sky would not be a fixed dome. It would be a very slow dance floor, though probably not one where anyone wants to request a faster song. The measurements that reveal this motion are quiet and precise. They come from radio spectra, stellar positions, parallax, proper motions, radial velocities, models, and comparisons. No single observation says everything. The case is built piece by piece. Gas velocities show movement along our line of sight. Young clusters show how recently formed stars travel in 3 dimensions. The mapped structure shows where the wave lies. The model links position and motion. Each piece alone is limited. Together they create a picture of a wave that is not only shaped like a ripple, but appears to be moving like one. This is a different kind of wonder from seeing a bright nebula in a telescope. It is quieter, more data-shaped, and perhaps a little more modern. The beauty is not only in the image, but in the reconstruction. The universe did not give us a simple video of the Radcliffe Wave waving. Astronomers had to build the video from clues. They had to use young stars as memory traces of gas. They had to use molecular lines as motion markers. They had to place everything into a 3-dimensional map. It is patient work, but patient work is often how the largest hidden patterns become visible. So yes, the Radcliffe Wave appears to be moving through space, but not in the sudden way the phrase might first suggest. It is oscillating through the Milky Way's disk, rising and falling under the influence of galactic gravity, while also drifting outward from the centre of the galaxy. It is not simply a curve. It is a structure with motion. It is a giant nearby feature whose gas and young stars help trace the local galaxy's dynamics. It reminds us that the Milky Way is not a flat, still painting. It is a moving system, and we are inside it. If this enormous wave lies near the Sun, and if the Sun itself is moving around the galaxy and bobbing through the disk, then have we ever crossed paths with the Radcliffe Wave? Has the solar system passed through material connected to it, or near enough to be affected by its neighbourhood? The Sun does move. It orbits the centre of the Milky Way. It drifts through different interstellar environments. It passes through regions that are thinner, denser, hotter, colder, quieter, or more disturbed. And over millions of years, those changes can matter. The first thing to remember is that the solar system is not parked. It can feel that way because from our daily view, the sun rises, the seasons turn, and the stars seem to return to familiar places year after year. But that calm is only local. Earth orbits the sun. The sun carries Earth, the planets, the asteroids, the Kuiper Belt, the distant icy objects, and all the small dusty leftovers around the galaxy. Our whole solar system is moving through the Milky Way at roughly hundreds of kilometers per second, tracing a long orbit around the galactic centre. On top of that orbit, the sun also moves up and down through the galaxy's disk, passing above and below the average plane over long timescales. It is not a flat ride. It is more like a slow galactic carousel, except the music takes millions of years per verse, and nobody quite knows where the operator is. So when we ask whether the solar system passed through the Radcliffe Wave, we're asking a question about two moving things. We're not comparing a fixed sun to a fixed wave. The sun has a past path. The wave has motion too. The gas clouds and young stars associated with it move under the influence of the Milky Way's gravity. The structure appears to oscillate through the galactic plane and drift outward from the galactic centre. To reconstruct a possible encounter, astronomers have to rewind both sides of the story. Where was the sun millions of years ago? Where was the relevant part of the Radcliffe Wave then? Did their paths overlap closely enough to count as a crossing? That is a harder problem than it sounds. You cannot simply draw a straight line backward from the sun and another line from the wave, because galactic orbits curve. Stars respond to gravity from the Milky Way. Gas clouds do not behave like solid balls. Clusters disperse. Measurements have uncertainties. The further backward you go, the more those uncertainties grow. It is a little like trying to reconstruct the path of a leaf floating in a river by looking at where it is now, where the nearby ripples are now, and where some other leaves might have been last week. Except the river is the Milky Way, the leaf is the sun, and last week is 15 million years ago. Astronomy does enjoy making simple tasks larger. Researchers approach this by using young open clusters associated with the Radcliffe Wave as tracers. Open clusters are groups of stars born together from the same cloud. They're useful because their stars share a common origin, and if the cluster is young enough, it can still tell us something about the gas structure from which it formed. In the case of the Radcliffe Wave, young clusters help trace the movement of the wave's star-forming regions. By looking at where those clusters are now, how old they are, and how they are moving, astronomers can estimate where parts of the wave were in the past. The Sun's orbit can also be traced backward using models of the Milky Way's gravitational field. The Sun has a current position and velocity, and from those, scientists can calculate a probable past path. It is not perfect, because the galaxy is not a perfectly smooth machine. But over the last few tens of millions of years, the reconstruction can be good enough to ask meaningful questions. The study that examined this found that the solar system's past trajectory appears to intersect the Radcliffe Wave in the Orion region. The estimated timing falls roughly between 18 and a little over 11 million years ago, with the closest approach likely somewhere around 15 to 12 million years ago. That is recent in galactic time, but ancient in human terms. There were no humans then. There were no cities, no telescopes, no people lying awake wondering if a wave of gas had passed nearby. Earth was in the Miocene epoch, a period when mammals were diversifying, grasslands were spreading in many places, and the climate system was undergoing long-term changes. The continents were in recognizable but not identical positions. Life on Earth was already rich and complicated, but the familiar human world had not yet begun. If the solar system passed through the Radcliffe Wave then, It did so silently, with no one standing under the sky to notice. But what does pass through actually mean here? It does not mean Earth plunged through a thick visible wall of cloud. Molecular clouds are enormous but extremely diffuse by everyday standards. Even dense interstellar clouds have densities far lower than anything we would call air. If you could somehow scoop up a cubic centimetre of a molecular cloud, it might contain hundreds or thousands of particles, which sounds like a lot until you compare it with air at sea level on Earth, where a cubic centimetre contains around tens of quintillions of molecules. By human standards, interstellar clouds are almost nothing. By galactic standards, they are thick enough to matter. This is the kind of scale shift astronomy asks of us again and again. The solar system is also protected by the heliosphere, a vast bubble created by the solar wind. The sun constantly sends charged particles outward, and this flow pushes against the surrounding interstellar medium. Where the solar wind meets the material between stars, a boundary forms. That boundary is not a solid shell, but it marks the region where the sun's influence gives way to the wider galaxy. The heliosphere helps shield the planets from some interstellar particles and cosmic rays. Its size and shape depend on the pressure of the material outside it. If the solar system moves into a denser region of interstellar gas, the heliosphere can be compressed. If the surrounding medium is thinner, it can expand. This is where a Radcliffe Wave crossing becomes interesting. If the sun passed through denser gas associated with the wave, the heliosphere may have shrunk. A smaller heliosphere could allow more interstellar dust and cosmic rays into the inner solar system. Some of that dust might eventually reach Earth's atmosphere. Changes in cosmic ray exposure and dust influx are the kinds of things scientists can look for indirectly, through isotopes and other traces preserved in geological records. This does not mean the Radcliffe Wave definitely changed Earth's climate. That would be too strong. But it does mean that a crossing could, in principle, have left clues. There is a cautious link here with Earth's climate history. The estimated timing of the possible crossing overlaps with the Middle Miocene climate transition, a period when Earth cooled and Antarctic ice expanded. That overlap is intriguing. It makes scientists ask whether the galactic environment could have played some role, or whether the timing is only coincidence. And this is where we have to be careful, because coincidence is not proof. Earth's climate is shaped by many powerful factors: greenhouse gases, ocean circulation, tectonics, orbital cycles, ice feedbacks, volcanic activity, and long-term carbon cycle changes. A possible passage through a galactic gas structure would have to be tested against all of that. The galaxy may have been part of the background, but Earth's climate is not a simple instrument that plays one note when space taps it. Still, the possibility is worth studying because it connects fields that do not usually sit at the same table. Galactic astronomy, heliophysics, geology, paleoclimate, and nuclear astrophysics all become part of the same question. Did the Sun's journey through the Milky Way leave measurable marks on Earth? Could certain radionuclide signals, such as unusual isotopes created or delivered by nearby cosmic events, help trace encounters with interstellar material? Could dust influx have changed during a passage through a denser cloud? These are difficult questions, but they are wonderfully concrete. They do not ask whether space feels meaningful. They ask whether atoms in rocks, sediments, or ice might remember where the sun has been. The Orion region matters in this reconstruction because it is one of the great star-forming regions associated with the Radcliffe Wave. Orion is already familiar from earlier in our journey. A bright winter constellation to the eye, but a deep physical complex in space. The Orion molecular cloud complex contains gas, dust, young stars, and nebulae. If the sun's past path intersected the Radcliffe Wave in the Orion portion, then our solar system may have moved through or near material connected to one of the most famous stellar nursery regions in the sky. There is something quietly astonishing about that. The same direction where many of us can find Orion's belt may also point toward a region tied to a past environment our solar system crossed millions of years ago. Of course, the sky direction today is not a simple snapshot of the past crossing. The sun has moved, the clouds have moved, the stars have moved, the galaxy has rotated. We are not looking at a fixed scene preserved since the Miocene. This is why models are needed. Astronomers reconstruct trajectories through a dynamic galaxy. They take current positions and velocities, then use gravitational models to estimate past locations. It is not time travel in the science fiction sense, but it is a kind of mathematical archaeology. Instead of digging through soil, scientists dig through motion. The local bubble adds another nearby piece to this story. Our solar system currently sits inside a cavity of hot, low-density gas. This bubble was likely carved by a series of supernova explosions from massive stars over the past several million years. Its walls are associated with many nearby young stars and star-forming regions. Earlier work has suggested that the expansion of the local bubble helped gather gas on its surface, where star formation has occurred. If the massive stars that made the bubble were born in or near the Radcliffe Wave, then the wave could be connected indirectly to the very cavity we now occupy. This would make the local neighbourhood a layered history. Gas organised into a wave, stars born along it, massive stars exploding, a bubble opening, and the sun travelling through the result. Imagine the solar system moving through that history like a small lantern, carried across a vast landscape. The landscape itself changes. Clouds gather and disperse. Stars form and die. Bubbles expand. The sun does not control the scene. It passes through it. For most of its life, the sun has orbited the galaxy quietly, while Earth has carried oceans, continents, ice, forests, deserts, microbes, animals, and eventually the complicated little creatures who invented calendars and then complained about being busy. All the while, the solar system has been moving through the interstellar medium, encountering different conditions so gently and slowly that only deep records and careful models can reveal them. If the crossing happened, it would not have been a single instant. A structure like the Radcliffe Wave is broad and uneven. The sun's encounter would have unfolded over time, perhaps over hundreds of thousands or millions of years depending on the region and density involved. It would not be like crossing a border at a checkpoint with the solar system handing over a passport and being told to declare any fruit. The interstellar medium changes gradually. Density rises and falls. Dust concentrations vary. Magnetic fields and cloud structures complicate the boundary. A crossing is more like passing through a long region of different weather than stepping through a doorway. That slow passage may have compressed the heliosphere if the surrounding gas was dense enough. A compressed heliosphere could expose the outer planets, and perhaps even parts of the inner solar system, to more interstellar material. Some studies of dense cloud encounters suggest that under extreme conditions, the heliosphere might shrink dramatically. Whether the Radcliffe Wave encounter reached that level is part of the careful scientific question. The answer depends on the density of the material encountered, the sun's motion, the structure of the cloud, and the state of the solar wind at the time. We do not have a simple photograph of the encounter, only models and clues. This is why the phrase "could have affected Earth" should be spoken softly. It is possible to imagine mechanisms. More interstellar dust could enter the solar system. Cosmic ray flux might change if shielding changed. Atmospheric chemistry or cloud formation could be influenced in small or large ways, depending on the strength and duration of the exposure. But connecting any of that directly to a major climate transition is hard. Earth is not a passive ball waiting for the galaxy to adjust its thermostat. It has oceans, atmosphere, continents, life, carbon cycles, and orbital variations. The Middle Miocene cooling has strong Earth-based explanations as well. The galactic encounter, if it occurred, may be a contributing factor, a coincidental overlap, or a clue to look for in radionuclide records. it is not yet a settled cause, that uncertainty is not disappointing. It is part of what makes the story good science. A sensational version would say, the Radcliffe Wave changed Earth's climate. A careful version says, the timing of a possible solar system passage through the Radcliffe Wave overlaps with a major climate transition, and the physical effects of such a crossing are worth investigating. The careful version is less dramatic, but it is stronger. It leaves room for data. It lets geology answer where geology can answer. It lets astronomy provide the trajectory. It lets heliophysics model the shielding. It does not force the universe to be simpler than it is. There is also a deeper lesson here about the relationship between Earth and the galaxy. We often think of Earth's environment as beginning with the atmosphere and ending somewhere near the Moon. Then we learn about the solar wind, the magnetosphere, solar storms and cosmic rays, and the boundary expands. Then we learn that the Sun itself moves through different interstellar environments, and the boundary expands again. Earth is not sealed away from the galaxy. It is protected, yes. The atmosphere protects the surface. The magnetic field helps shield charged particles. The heliosphere pushes back against the interstellar medium, but protection is not separation. The larger galaxy is still part of the setting in which our planet lives. A passage through the Radcliffe Wave, if confirmed in more detail, would be one example of that larger setting. The solar system's path through the Milky Way may sometimes bring it into contact with denser clouds or energetic regions. Nearby supernovae can deposit isotopes on Earth. Changes in cosmic ray exposure can be studied. Interstellar dust can enter the solar system. Most of the time, these effects are subtle, especially compared with the powerful internal systems of Earth. But subtle does not mean irrelevant. Over long times, small influences can leave traces. For the sleepy mind, there is something wonderful about imagining Earth during that possible crossing. Not because of disaster, but because of continuity. The planet was already old. Life had already transformed the atmosphere long before. Mammals were evolving. Forests, grasslands, oceans, and ice sheets were changing. Above all of it, the Sun moved quietly through the galaxy, perhaps passing through denser material associated with a great wave of star-forming clouds. No creature knew, no sky sign appeared. The encounter, if it happened, was written not in headlines but in particles, pressures, dust grains, and perhaps faint chemical memories. The study of such a crossing also depends on young clusters along the Radcliffe Wave, because those clusters act as time markers. If a cluster is young and associated with the wave, its present position and velocity can help reconstruct the wave's past. By selecting high-quality clusters with reliable ages and motions, researchers can trace the wave backward over the last 30 million years. Then they can compare that reconstruction with the Sun's past orbit. This is a careful matching exercise. It asks whether the paths intersect within uncertainties. It is not a perfect rewind button, but it is a meaningful one. The result, as currently reported, is that the solar system's trajectory did intersect the Radcliffe Wave in the Orion region. That does not mean every detail is settled. Other teams may refine the timing, improve the cluster sample, adjust the galactic potential model, or revise the density estimates of the gas encountered. The wave itself may not behave like a perfectly coherent solid structure, and its past shape may have changed through galactic shear and cloud evolution. These complications matter. They remind us that the crossing is an active research result, not an ancient fact carved permanently into stone, but it is a serious result and it opens a fascinating path. One of the most interesting future tests may come from looking for radionuclide anomalies. Certain radioactive isotopes can be produced by supernovae or cosmic ray interactions, and some can be deposited on Earth. For example, Iron-60 has been found in geological records and is often discussed as evidence for nearby supernova activity in the relatively recent geological past. Other isotopes may help trace changes in cosmic ray exposure or interstellar dust influx. If a Radcliffe Wave crossing increased the amount of material reaching Earth, there might be subtle signals preserved in marine sediments, crusts, or ice. Finding them, dating them, and connecting them to a specific galactic event is not easy. Rocks are patient, but they do not label their evidence as clearly as one might like. That kind of work is powerful because it turns the solar system's galactic journey into something testable. The sun's path is not just a line in a simulation. It may have physical consequences recorded on Earth. The challenge is separating those consequences from everything else happening on the planet. Climate shifts can have many causes. Isotopic signals can have multiple sources. Dating uncertainties can overlap. But if astronomy predicts a certain time window, geology can look there. If geology finds a signal, astronomy can ask what nearby events might explain it. This is how distant fields begin to talk to each other, politely at first, then with more diagrams. So did our solar system pass through the Radcliffe Wave? The best current answer is that it may well have, and recent research suggests it likely intersected the wave in the Orion region during the Middle Miocene, roughly 15 to 12 million years ago at closest approach. But the consequences of that passage remain uncertain. It may have compressed the heliosphere. It may have increased interstellar dust entering the solar system. It may have left signals worth searching for. It may have coincided with climate changes on Earth without causing them. The encounter is not a simple explanation for Earth history, but it is a new and intriguing piece of the setting, and perhaps that is enough for now. The sun has not always travelled through the same kind of space. Our planet's long history has unfolded not only within the solar system, but within the changing environment of the Milky Way. The Radcliffe Wave gives us a nearby example of that galactic environment, and the possibility that we pass through it makes the story feel less like a distant map and more like a route we have actually taken. If the Radcliffe Wave is real, if it moves, if it carries stellar nurseries, and if the sun may have crossed part of it in the past, then what made such a structure in the first place? Was it shaped by explosions from massive stars, by the slow pull of galactic gravity, by the motion of spiral arms, by a passing disturbance, or by several forces working together over millions of years? The mystery of what created the Radcliffe Wave is where the story becomes less like drawing a map and more like reconstructing an old event from footprints in soft ground. We can see the structure now. We can trace its cold clouds. We can measure young stars along it. We can detect signs that it is moving, or at least that many of its parts behave as if they belong to a larger oscillating pattern. But asking what made it means turning the whole picture backward. Something, or perhaps several things together, bent the galaxy's gas into this long, raised, dipping form. Something arranged dense clouds across thousands of light years. Something gave the local Milky Way a shape that looks, from the right angle, like a ripple. And the honest answer is that astronomers do not yet know for certain. That may sound unsatisfying at first, but it is actually a very good place for science to be. A mystery with measurements is not an empty mystery. It has edges, it has clues, it has suspects. The Radcliffe Wave is not just a strange word attached to a vague shape. It has distance, length, width, velocity, young clusters, gas maps, and possible connections to nearby structures like the local bubble. So the question is not floating in the dark with nowhere to land. It has a real body. It has evidence. What it does not yet have is one simple explanation that everyone can point to and say, yes, that is definitely what bent the clouds. One possible idea is that the wave was shaped by gravity in the Milky Way itself. The galaxy is not a rigid disk. It is a rotating system of stars, gas, dust, dark matter, and magnetic fields, all moving through a gravitational field that is smooth in some ways and uneven in others. Gas in the disk can be lifted above the midplane, pulled back down, and set into long, vertical motions. If the Radcliffe Wave is oscillating through the galactic plane, as recent studies suggest, then gravity is not just part of the background. It is part of the wave's behaviour. The Milky Way's gravitational field may act like a restoring influence. When gas is displaced upward or downward, gravity pulls it back toward the disk, and the material can move through the plane in a slow oscillation. A simple comparison might be a swing, though an enormous and extremely slow one. Pull a swing away from its resting position and let go, and gravity pulls it back. It passes through the middle, rises on the other side, and continues. The Radcliffe Wave is not a swing, of course. It is not made of a single solid object, and no one has attached it to a tree in the galactic playground. But the idea of displacement and return is useful. If gas clouds are pushed away from the midplane, the galaxy's gravity can guide them back. The result may be an up and down motion spread along a large structure. But that only moves the question back one step. If gravity helps the wave oscillate, what pushed the gas out of place to begin with? A restoring force explains how a disturbance can continue, but not necessarily what started it. A swing moves because someone pushed it. A guitar string vibrates because someone plucked it. A pond ripples because a stone, a breeze, or a duck with poor landing skills disturbed it. In the Milky Way, the push might come from several possible sources. One suspect is stellar feedback. This is the general name for all the ways stars return energy and momentum to their surroundings. Massive stars are especially influential. They shine with intense ultraviolet radiation. They blow strong stellar winds. At the ends of their short lives, they explode as supernovae. These events can carve bubbles in interstellar gas, sweep material into shells, compress clouds, and trigger new rounds of star formation. In our local neighbourhood, this is not just theory. The Sun currently sits inside the local bubble, a cavity of hot, thin gas likely created by a series of supernova explosions over the last several million years. The walls of that bubble are connected to nearby star-forming regions. So when we think about what bends and gathers gas near the Sun, supernovae are hard to ignore. They are the galaxy's most dramatic way of rearranging furniture. Imagine a group of massive stars born in or near a dense cloud. They live fast, bright lives. Their radiation begins to clear gas around them. Their winds push outward. Then, one after another, some explode. Each supernova sends a shock wave through the surrounding medium. Gas is pushed aside. A cavity grows. The swept-up material collects along the edges. In places, that compressed material may become dense enough to form more stars. Over time, a chain of explosions can sculpt a region hundreds of light years across. Now scale that up, connect it with pre-existing clouds and galactic motion, and you begin to see why stellar feedback is such a tempting explanation for nearby structures. Could supernovae have created the Radcliffe Wave itself? Perhaps they helped shape parts of it, but it is not obvious that they alone can explain the whole structure. The Radcliffe Wave is thousands of light years long. It is very extended, much longer than a simple local bubble. Supernovae can carve large cavities and shells, but arranging a coherent wave across such a vast length may require something more than a cluster of explosions in one place, or it may require many feedback events interacting with the gas over time. The difficulty is not whether supernovae can move gas. They absolutely can. The difficulty is whether they can create this particular long, wavy, coherent arrangement. Another clue comes from the possible connection between the Radcliffe Wave and the local bubble. Recent motion studies suggest that the cluster whose supernovae eventually created the expanding local bubble may have been born in the Radcliffe Wave. If so, the relationship could be layered. The wave may have helped form massive stars. Those stars later exploded and made the local bubble. The bubble then reshaped nearby gas and may have influenced star formation along its surface. In that case, the Radcliffe Wave would not simply be a product of the local bubble. It could be an older structure that gave birth to some of the stars that later carved the bubble we live inside. The cause and effect would not be a straight line. It would be more like a family tree with several branches folding back near each other. This is one of the reasons the origin problem is tricky. In space, structures make other structures. A cloud forms stars. Stars blow bubbles. Bubbles compress clouds. Compressed clouds form more stars. Galactic rotation stretches everything. gravity bends it. Magnetic fields resist and guide motion. By the time we arrive with our telescopes and ask, who made this shape? The answer may be several things at different times, in different places, and none of them kept receipts. Very inconsiderate, really. A second major possibility involves larger galactic dynamics. The Milky Way's disk is full of motions caused by its spiral arms, rotating pattern, and gravitational structure. Gas does not simply orbit as a smooth circular ring. It can be compressed in spiral arms, stretched by shear, gathered into filaments, and disturbed by the uneven gravitational pull of stars and dark matter. The Radcliffe Wave lies in the local arm region, sometimes called the Orion Arm or local arm. Spiral arm-related dynamics could help organize gas into long structures. If gas enters a spiral arm or a spur, it may be compressed, slowed, stretched, and gathered into clouds. Star formation may then light up the denser parts. This idea treats the Radcliffe Wave less like a single scar from one explosion, and more like a feature of galactic weather. Just as Earth's atmosphere has jet streams, fronts, and cloud bands shaped by rotation and pressure, the Milky Way has gas flows shaped by gravity and rotation. The comparison is not exact, because interstellar gas is thinner, magnetized, and governed by different conditions, but it helps. A cloud band on Earth is not caused by one raindrop. It forms from large-scale motion. The Radcliffe Wave might also be the result of large-scale gas dynamics rather than one dramatic local event. Galactic shear is especially important. The Milky Way rotates differentially, meaning different parts of the disk orbit at different speeds. Gas closer to the centre generally moves around the galaxy differently from gas farther out. This can stretch structures over time. A cloud complex that begins as a shorter feature can be pulled into a longer one. Filaments can be elongated. Old shapes can be distorted. This is one reason some researchers caution against treating the Radcliffe Wave as if it were a single solid object oscillating neatly through the disk. It is made of gas and clouds, and gas is not known for respecting tidy boundaries. Galactic shear can stretch, twist, and complicate the wave on timescales comparable to its possible oscillation. That complication does not make the wave less real. It makes it more realistic. A real structure in the interstellar medium should be messy. It should evolve. It should be affected by rotation, gravity, turbulence, and feedback. The question is whether the wave's current shape is mostly a snapshot of one coherent oscillation, or partly the result of gas being stretched and rearranged by ordinary galactic motions. The answer may be both. The wave may have been disturbed vertically, while shear and local gas flows lengthened and reshaped it. Nature is very fond of answering both when we ask it to choose. A third possibility is that something outside the local gas disturbed the Milky Way's disk. The galaxy has not lived in isolation. Smaller galaxies orbit it, pass near it, and sometimes merge with it. The Sagittarius dwarf galaxy, for example, has interacted with the Milky Way over time and is often discussed as a possible driver of large-scale ripples and waves in the galactic disk. When a smaller galaxy passes through or near the disk, its gravity can disturb stars and gas, creating vertical waves, warps, and oscillations. It is not like a pebble thrown into a pond in a simple way, but the idea of a gravitational disturbance spreading through a disk is useful. Could the Radcliffe Wave be a local trace of such a disturbance? Some studies have suggested that the vertical extent and wave-like velocity pattern could point to a perturbation, perhaps from something like a passing dwarf galaxy. This is intriguing because it connects our local cloud structure to the Milky Way's larger history of interactions. The gas near the Sun might carry the memory of a gravitational nudge from a much larger event. That is a wonderfully strange thought. A nearby chain of star-forming clouds may have been bent by a disturbance from a satellite galaxy, the way a blanket can wrinkle when someone tugs one corner from across the bed. But this idea also has challenges. A dwarf galaxy perturbation would need to produce the right scale, timing, and local effect. The Radcliffe Wave is specific. It has a particular location, length and motion. Large-scale disturbances can create many patterns, and matching one observed structure to one past interaction is difficult. The Milky Way has many moving parts. A ripple in the disk may have multiple causes, and the same observation can sometimes be explained by more than one model. So while an external perturbation remains a serious possibility, it is not a confirmed answer. Then there is the role of magnetic fields. The interstellar medium is threaded by magnetic fields that can influence how gas moves and collapses. Magnetic fields can support clouds against collapse, guide charged particles, and affect the shape of filaments. In molecular clouds, they interact with turbulence and gravity in complicated ways. On large scales, magnetic fields may help organize gas into elongated structures or resist certain motions. They are difficult to measure in full detail, which makes them both scientifically important and mildly annoying, like a character in a mystery novel who clearly knows something but refuses to speak plainly. Could magnetic fields help shape the Radcliffe Wave? Possibly, especially on smaller cloud and filament scales. They may influence how the gas is gathered, how dense regions align, and how material responds to shocks or compression. But magnetic fields alone are unlikely to be the whole explanation for a structure thousands of light years long. More likely, they are one ingredient in the recipe. The wave's origin probably involves gravity and gas dynamics first, with magnetic fields shaping the details. Turbulence is another ingredient. Interstellar gas is turbulent, meaning its motion is chaotic across many scales. Turbulence can create filaments, compressions, and density variations. It can help form dense clumps, but it can also prevent gas from collapsing too quickly. In a molecular cloud, turbulence is central to the internal structure. Across a giant wave, turbulence may add irregularity and texture. But again, turbulence by itself may not explain the coherent large-scale undulation. It is more likely part of the cloud-level messiness layered on top of a larger galactic disturbance or flow. A useful way to think about all these possibilities is to imagine the Radcliffe Wave as the result of several sculptors working on the same material. Galactic gravity lifts and pulls, spiral arm dynamics gather and compress, supernovae carve and push, shear stretches. Magnetic fields guide. Turbulence roughens. A passing dwarf galaxy may have given the disk a shove. The final shape we see today may not have one creator. It may be the outcome of many processes acting together over tens of millions of years. This is common in astronomy. We often want a single origin story because single stories are easier to remember. A crater was made by an impact. A supernova remnant was made by an exploding star. A planet formed in a disk. But large interstellar structures are often less tidy. They are not made in one clean event. They are assembled, disturbed, stretched, compressed, and partly erased while still forming stars. The Radcliffe Wave may be a process as much as an object. It may be something the galaxy is doing, not merely something the galaxy did. The timing matters as well. If the wave is oscillating, it has a period, a time scale over which it rises and falls through the galactic plane. If shear can stretch it significantly in tens of millions of years, then the wave may not survive unchanged for very long. That means the structure we see today may be relatively young in galactic terms. Young here still means millions of years old, because astronomy uses youth the way some people use just a minute when looking for keys. The wave may have formed, evolved, and become recognizable over a timescale connected to nearby star formation and local bubble history. The motion of young clusters can help constrain this. If clusters along the wave have ages and motions that line up with a shared pattern, they preserve clues about when the structure was active in forming stars. Gas velocities tell us how the clouds move now. Numerical simulations can test whether certain initial disturbances evolve into something like the Radcliffe Wave. If a model of a dwarf galaxy perturbation produces a similar vertical oscillation, that supports one idea. If simulations of shear and epicyclic motion reproduce the wave's length and shape, that supports another. If feedback models create the right bubbles and compressed shells, that adds another piece. The goal is not to guess beautifully. It is to build a model that survives contact with the data. This is where the Radcliffe Wave becomes more than a local curiosity. It offers a test case for how interstellar gas evolves in a spiral galaxy. Because it is nearby, astronomers can measure it in unusually rich detail. They can study its clouds, young stars, gas motion, dust structure, and relationship to the local bubble. Many other galaxies show filaments and waves in their gas, but they're too far away for this level of close inspection. The Radcliffe Wave is like finding a working sample of galactic structure in our backyard. A very large backyard, yes, and one where the fence is several thousand light years long, but still nearby enough to study. There is also a reason not to imagine the wave as perfectly permanent. Gas clouds form and disperse. Star formation consumes and disrupts material. Massive stars alter their surroundings. Galactic rotation stretches structures. Over time, the Radcliffe Wave may lose its current shape, merge with other filaments, or be transformed beyond recognition. Future astronomers, millions of years from now, may not see the same structure we map today. They may see different clouds, different bubbles, different stellar associations. The Milky Way is not a museum. It is more like a kitchen, where ingredients are constantly being stirred, heated, cooled, spilled, reused, and occasionally exploded. So what could have created such a vast galactic wave? The safest answer is a combination of processes. A disturbance likely displaced gas from the galactic plane. The Milky Way's gravity may now be guiding the gas in an oscillation. Spiral arm and local arm dynamics may have gathered and stretched the material. Supernovae and stellar winds may have carved nearby cavities and reshaped parts of the structure. Galactic shear may be changing it even now. An external perturbation, perhaps from a dwarf galaxy interaction, remains a possible larger trigger. The wave may not have a single birthplace. It may be the visible result of the local galaxy responding to motion, pressure, gravity, and time. And perhaps that is more interesting than a single answer. A single answer would close the case too neatly. The real Radcliffe Wave is teaching astronomers how complicated the solar neighbourhood is. It says that the gas near the Sun has been bent, lifted, stretched and stirred. It says that star formation happens inside structures shaped by the whole galaxy, not only inside isolated clouds. It says that the Milky Way's disk is not a still flat surface, but a moving layer where disturbances can travel, fade and leave behind new stars. From our small viewpoint, the wave feels almost impossibly large, but to the Milky Way, it may be one local fold among many. A bend in the gas, a ripple in a disk that has been disturbed before and will be disturbed again. Our Sun happens to be close enough for us to notice this one in great detail. That closeness is a gift. It lets us study how clouds become connected, how young stars trace motion, how bubbles and waves may share a history, and how our own neighbourhood fits into the larger structure of the local arm. Placing the Sun inside the Orion Arm sounds simple at first, almost like giving our solar system a street address. Earth is in the solar system. The solar system is in the Milky Way. The Sun sits in the Orion Arm. There we are. Cosmic mail delivered. But as soon as we ask what the Orion Arm actually is, and how our neighbourhood fits inside it, the address becomes much more interesting. Because the Orion Arm is not a clean road with painted lanes. It is not a solid bridge between bigger spiral arms. It is a broad, uneven structure made of stars, gas, dust, stellar nurseries, young clusters, and older populations all moving around the galaxy together. And now, with the Radcliffe Wave mapped nearby, that local address has gained a surprising new feature. We may be living beside one of the main gas structures that helps define our part of the arm. For a long time, the Orion Arm was often treated as a minor feature, sometimes called the local spur. That word spur makes it sound small and temporary, like a little side road branching off between the grander highways of the Milky Way. The major spiral arms, such as Perseus and Sagittarius, received the larger role. They were the great lanes of stars and gas, the bright curving structures that help give a spiral galaxy its familiar form. The local arm where the Sun resides seemed less important, perhaps a modest bridge or spur between larger neighbours. A cosmic side street, you might say, with Earth parked somewhere along it, probably still wondering whether the permit is valid. But better measurements have made that older picture less satisfying. The local arm is not just a tiny random feature. It contains active star-forming regions. It stretches across thousands of light years. Its young stars and masses, which are natural radio sources associated with some star-forming regions, show that it has real structure and motion. It may be a branch of another arm, or it may be a more important segment than once assumed. The details are still studied and debated, but the idea of the Orion Arm as a small, unimportant spur has softened. Our local galactic neighbourhood has more substance than we used to give it credit for, which is a nice reminder that sometimes the place you live turns out to be more interesting after someone finally makes a better map. The Radcliffe Wave deepens that shift. It suggests that the gas in our part of the Milky Way is not arranged randomly. Instead, much of the nearby star-forming material lies along a long coherent wave, stretching through the local arm region. This matters because spiral arms are not made only of old stars. Their active life is tied to gas. Gas is where new stars form. Gas traces the places where the galaxy can still build. So if the Radcliffe Wave contains many of the nearby molecular clouds and star-forming complexes, it may be one of the key gas reservoirs of the Orion Arm. In plain terms, the wave may be part of the arm's working material, not just a decorative wrinkle. That is an important change in perspective. We are not merely beside a strange object. We are beside a structure that may help explain how our local arm is organised. The wave links stellar nurseries across large distances. It gives shape to the cold gas near the Sun. It may show where star formation is being fed, triggered, or arranged along the local arm. And because it lies close to us, it gives astronomers an unusually detailed laboratory for studying how spiral arm gas behaves from the inside. The Orion Arm itself is difficult to map because we are embedded within it. From outside the Milky Way, if we could hover above the galactic disk, perhaps with a cup of tea and a very sturdy chair, we might see the arms curling around the centre. We could trace where gas is thick, where young stars cluster, where dust lanes run, and where bright star-forming regions light up the disk. But from Earth, we do not have that overhead view. We look through the arm from within it. Nearby objects overlap with distant ones. Dust blocks and reddens starlight. The spiral pattern has to be reconstructed from distances, velocities, and tracers. This is why structures like the Radcliffe Wave are so valuable. They give local detail to a part of the arm we can study closely. A spiral arm is not a rigid object, like a metal spoke turning around a wheel. It is better thought of as a region where material is gathered, compressed, or organised by the galaxy's gravitational pattern. Gas can enter an arm, slow or compress, form molecular clouds, create stars, and then move on. Stars of different ages can appear offset from the densest gas because gas, newborn stars and older stars do not all trace the same exact path at the same time. In some external galaxies, astronomers see dust lanes, gas, and young bright stars arranged in layered patterns across spiral arms. Dense gas may sit on one side, and young stars may appear slightly downstream, showing where star formation followed gas compression. The Radcliffe Wave may allow astronomers to study a similar kind of relationship in our own local arm, but from a much closer view. That is why the placement of young massive stars and clusters near the Radcliffe Wave is so interesting. Some studies have found that luminous blue stars and young clusters are not simply sprinkled randomly around the wave. They appear inside and downstream from the gas structure. In everyday terms, the gas may mark where the raw material is concentrated, while the young stars show where that material has recently turned into light. The arrangement is not perfectly simple. because the Milky Way is not a tidy classroom demonstration. But the pattern suggests a relationship between the wave and the star formation that helps define the Orion Arm. This gives us a more dynamic picture of home. The Sun sits in a local region that is not just between major spiral arms like an empty gap. It is part of a working structure where gas and young stars trace a real piece of the Milky Way's disk. The Radcliffe Wave may be one of the closest and clearest signs of that structure. It says that the local arm is not only a name on a diagram, it has a gas backbone, or at least a long gas feature, where many nearby stellar nurseries are arranged. That does not mean the wave is the entire Orion Arm. The arm is broader, more complex, and contains many stellar populations. But the wave may be one of its most important local gas components. Think of the Orion Arm as a wide countryside, and the Radcliffe Wave as a long river valley running through part of it. The countryside includes towns, roads, fields, old buildings, and hills. The river valley is not everything, but it shapes where life gathers, where roots form, and where activity concentrates. In the Milky Way, the gas plays that role for star formation. Where cold molecular gas gathers, new stars can form. The Radcliffe Wave may be one of the local valleys where the Milky Way's future stars are being assembled. Our solar system, however, is not inside one of the dense star-forming clouds right now. We live in a relatively low-density cavity called the local bubble, surrounded by denser material and nearby star-forming regions. This is another important part of our location. We're not sitting in the thickest part of the Radcliffe Wave. We are near it, close enough that it shapes the local map but not embedded in a bright stellar nursery like Orion. That is probably fortunate. Dense star-forming regions can be beautiful, but they are also full of radiation, massive young stars and future supernovae. The Sun's current neighbourhood is comparatively quiet, a little bubble of thin, hot gas surrounded by the busier regions where the galaxy continues building stars. It is rather like living on a quiet side lane near a large construction site. You can hear the work in the distance, but nobody is drilling through your kitchen wall at breakfast. The relationship between the local bubble and the Radcliffe Wave makes our place even more interesting. The bubble was likely carved by a series of supernova explosions from massive stars. Some research suggests those massive stars may have been born in a moving group associated with the Radcliffe Wave. If that connection holds, then our current low-density neighbourhood may have been shaped by stars that formed along the very gas structure we are studying. The wave helped form stars. Some of those stars exploded. Their explosions cleared a cavity. The Sun now sits inside that cavity. This is not a simple, straight story, but it is a connected one. Our local address is written in gas, stars, explosions, and motion. There is a humbling detail here. The Sun is not young compared with these local star-forming regions. It formed about 4.6 billion years ago, long before the present structure of nearby clouds looked the way it does now. The Sun has orbited the Milky Way many times, moving far from its birthplace. The Radcliffe Wave, as we see it, is a more recent local feature in the life of the galaxy. So we should not imagine the wave as the Sun's birthplace. It is not our cradle. It is more like a nearby active region in the neighbourhood through which the Sun is currently travelling. The solar system is an older traveller passing beside younger nurseries. That contrast helps place us in time as well as space. The Orion Arm contains both old stars and fresh star-forming gas. The Sun belongs to the older population, a middle-aged star moving quietly through the disk. Along the Radcliffe Wave, new stars are forming now or have formed recently. Some of those stars may still be surrounded by protoplanetary disks. Some may eventually host planets. Some massive ones will live fast and end explosively. Our own system, with its mature planets and long biological history on Earth, is passing through a region where other systems are just beginning. It is a galactic neighbourhood with many ages living side by side. This is one of the most useful things the Radcliffe Wave reveals. It shows that our place in the Orion Arm is not only a coordinate, it is a context. We sit near a major chain of star-forming gas. We live inside a bubble likely carved by past supernova. We're close to famous molecular clouds that are part of a larger wave-shaped structure. The local arm is not just stars sprinkled around the sun. It is a layered environment with cavities, clouds, filaments, young clusters, and long motions through the disk. The Orion Arm's position between the Sagittarius and Perseus arms also matters. In older diagrams, our region can look like a small bridge between those larger arms. But the more astronomers measure star-forming regions, masses, young stars, and gas, the more the local arm looks like a serious structure in its own right. It may not be as grand as some major arms across the galaxy, but it is not nothing. The Radcliffe Wave strengthens that impression because it provides a coherent gas structure running through part of the arm. It is evidence that our local region has organised star-forming material over a large scale. For astronomers, this is valuable because the Milky Way is hard to compare with other spiral galaxies from the inside. We see external galaxies as whole systems, but we see our own in great local detail. That is both a blessing and a nuisance. With other galaxies, we can see the big pattern but not the fine detail. With the Milky Way, we can see nearby details but struggle with the big pattern. The Radcliffe Wave helps bridge those views. It is a local structure big enough to matter for spiral arm studies and close enough to measure in detail. It lets scientists ask whether the arrangement of gas and young stars in our own arm resembles patterns seen in external galaxies, where star formation appears downstream from gas compression. In that sense, the Radcliffe Wave is like finding one small but detailed section of a machine whose full shape is hard to see. If you can study how that section works, you may understand more about the whole machine. The Orion Arm is part of the Milky Way's spiral structure. The Radcliffe Wave may show how gas gathers within that arm, how young stars appear near it, and how local feedback carves cavities around it. It is one of the closest places where galactic structure, molecular cloud formation, and star formation all meet in the same neighbourhood. The wave also changes the emotional map of the sky. Orion is no longer only a winter constellation with bright stars and a famous nebula. Taurus is no longer only a constellation with a red eye and dark clouds. Cygnus is no longer only the swan of summer skies. These familiar directions are linked by a physical structure, not by mythology, but by gas and distance. The constellations are human stories laid over the sky. The Radcliffe Wave is a real arrangement beneath those stories. Both can be meaningful, but they are meaningful in different ways. One helps us remember where to look, the other helps us understand what is there. For anyone who has ever looked up at Orion on a cold night, this is a lovely adjustment. The bright shape you know is only the visible front page. Behind it and around it lies a larger star-forming complex, and that complex belongs to a wave of gas stretching through the local arm. The familiar sky becomes part of a hidden structure. You do not need to see the whole wave with your eyes for it to be there. You only need to know that the stars and clouds have depth, and that depth has finally been mapped well enough to reveal a connection. This also helps correct a common misunderstanding about our location in the galaxy. When people hear that the solar system is in the Orion Arm, they may imagine that we are surrounded by a dense, bright spiral band. But the arm is not uniformly dense. It has clouds, gaps, bubbles, older stars, younger stars, and regions of different activity. The Sun's immediate surroundings are relatively quiet, while nearby regions are active. We are in the local bubble, near the Radcliffe Wave, within the broader local arm between larger spiral arms. That layered address is much more accurate than simply saying, we are in a spiral arm. It is also much more interesting, although admittedly less convenient for filling out forms. The Radcliffe Wave gives that layered address a physical anchor. It tells us where much of the nearby star-forming gas lies. It shows that the local molecular clouds are part of a coherent arrangement. It links our neighbourhood to the structure of the arm itself, and because it may be oscillating, it shows that this arm is not static. The gas is moving vertically through the disk, the sun moves as well. The local region has a history and a direction, not just a location. There is also a wider implication. If a structure like the Radcliffe Wave could remain hidden so close to us until modern three-dimensional mapping revealed it, then our picture of the Milky Way is still incomplete. Other structures may be waiting in the data. Some may be farther away, where dust and distance make mapping harder. Some may be nearby but confusing from our position. As Gaia and future surveys continue to improve distances, motions and chemistry, the Milky Way's local map will keep changing. Our address in the galaxy will become more detailed, and probably a little stranger because that is usually how better maps behave. This is not a reason to distrust the maps, it is a reason to appreciate how science improves. The old picture of a small local spur was useful. Newer measurements gave the local arm more respect. The Gould Belt helped organise nearby young stars and gas for many years. Then the Radcliffe Wave offered a better three-dimensional arrangement for much of the local star-forming material. Each step sharpened the view. The galaxy did not change. Our map did. What the Radcliffe Wave reveals, then, is that our place in the Orion Arm is active, structured and connected. We're not in a random quiet patch beside unrelated clouds. We are near a long gas feature that may trace the arm's star-forming reservoir. We are inside a bubble carved by past massive stars. We are close to clouds where new stars are forming now. We are moving through a disk that rises, falls, stretches, and responds to gravity. Our solar system setting is not simply space, it is a local galactic environment with a shape. That idea is concrete enough to hold even as you rest. The room around you is still, your bed or chair is still. Earth turns. Earth orbits the sun orbits the Milky Way inside the local arm. Nearby, the Radcliffe Wave stretches through that arm as a long chain of gas and stellar nurseries. Some parts glow with young stars, some parts remain dark and cold. Around us, the local bubble marks the after-effects of ancient supernovae. Above all of it, the galaxy turns, and the local gas continues its slow movement through the disk. It is easy to feel small in that picture, and we are small, but small does not mean disconnected. The atoms in Earth, in our bodies, and in the air we breathe were made by earlier generations of stars. The sun was born from a cloud like the clouds along the Radcliffe Wave, though not the same one. The galaxy continues making new stars nearby, using the same basic ingredients. Our place in the Orion Arm is not central in any grand sense, but it is deeply involved in the Milky Way's continuing process. We live in an old solar system beside young stellar nurseries, inside a bubble, near a wave, within an arm. That is a very different feeling from imagining space as empty blackness with stars scattered through it. The local galaxy has geography. It has neighbourhoods, it has histories, it has features that can be mapped, named, and studied. The Radcliffe Wave is one of those features. It is not the whole story of the Orion Arm, but it is one of the clearest local pieces we have found. It shows that the arm's gas is arranged in a way we did not recognise before. It gives us a better view of where the nearby star-forming clouds fit. And it turns our solar system's address into something richer than a dot on a diagram. By now, the Radcliffe Wave may feel less like a strange object with a distant name, and more like part of the scenery around home. Not home in the small sense, not the room around you, or the street outside, or the familiar shape of your town after dark, but home in the larger galactic sense. The sun, Earth, the planets, and every quiet evening we have ever known are moving through a region of the Milky Way that has texture. There are bubbles carved by old supernovae. There are clouds where new stars are still forming. There are young clusters drifting away from their birthplaces, and nearby, stretching across thousands of light years, there is a long wave of gas and dust that astronomers could only recognise once they learned how to map the local sky in 3 dimensions. That is a lovely thing to carry into rest, because it changes the feeling of the night sky without making it less peaceful. The stars above you are still the stars above you. Orion still rises when the season is right. Taurus still holds its place in the winter sky. Cygnus still crosses summer nights for many listeners in the Northern Hemisphere. The familiar constellations have not vanished. But beneath those old human patterns, there is a deeper physical arrangement. Some of the dark clouds and glowing nurseries scattered across those directions are connected. They are part of a larger structure, a wave-shaped chain of star-forming material near the Sun. For a long time, we did not see that connection. We saw pieces. Astronomers studied Orion, Taurus, Perseus, Cepheus and other regions as separate star-forming areas. They knew each one mattered. They knew these clouds were cold, dense, and full of the raw ingredients for stars. They knew young stars were being born inside them or had recently emerged from them. But the bigger shape stayed hidden because we were inside it. The sky flattened everything into a dome. Distance had to be measured. Dust had to be mapped. Stars had to be used like little lamps shining through fog. Only then did the local clouds fall into place, not as a neat ring around the Sun, but as a long undulating structure. That is one of the main lessons of the Radcliffe Wave. Sometimes the most important discoveries do not come from seeing something new, but from placing familiar things in the right positions. The universe does not always need to reveal a brand new light. Sometimes it only needs to give us a better map. A cloud we already knew becomes part of a larger chain. A famous nebula becomes one bright region along a hidden wave. A local star-forming complex becomes a clue to the shape of the Orion Arm. The galaxy was not changed by the discovery. Our understanding was. And what a strange understanding it is. Our solar system sits close to a vast wave-like structure, made of the same kind of material from which stars and planets can form. Not a solid wall, not a dangerous tide rushing toward Earth, not some dramatic cosmic ocean preparing to sweep us away. It is gas and dust, spread across distances so huge that even light takes thousands of years to cross them. It is dense by interstellar standards and almost empty by earthly standards. It is cold, wide, uneven and active in patches. Along it, stars are being born. Around it, older stars have already shaped the gas. Near it, our solar system travels inside the broader local arm. There is comfort in making that distinction. The Radcliffe Wave is enormous, but it is not a threat in the way the phrase giant wave might first suggest. Nothing is crashing over us tonight. There is no wall of gas arriving at the edge of the solar system like a storm front on a weather map. The wave is part of the Milky Way structure. It moves on timescales far beyond a human life. Its clouds drift, oscillate, stretch, and form stars over millions of years. To us, it is not an event. It is a setting. Still, settings matter. The place where something happens shapes the story. Earth's story is unfolded under the Sun, inside the heliosphere, within the local bubble, near the Radcliffe Wave in the Orion Arm, around the centre of the Milky Way. Each layer is real. Each layer adds context. You can describe Earth as a planet with oceans and continents, and that is true. You can describe it as the third planet from the Sun, and that is true too. You can describe it as a small rocky world moving through a solar system that may once have crossed material associated with a great galactic wave, and suddenly the same Earth feels placed inside a much larger room. The possible past crossing of the Radcliffe Wave is one of the more intriguing parts of the story, but it should be held carefully. The Sun's path through the Milky Way can be traced backward with models. The motions of young clusters associated with the wave can also be reconstructed. Recent work suggests that the solar system may have intersected the wave in the Orion region millions of years ago. If that happened, the surrounding interstellar material might have been denser than usual. The heliosphere may have been compressed. More dust or cosmic rays might have entered the solar system. Some of those effects might, in principle, leave traces on Earth. But there is a difference between a possible influence and a proven cause. Earth's climate has its own powerful machinery. Oceans move heat, continents shift, carbon cycles change, ice grows and melts, volcanic activity adds gases, Orbital cycles alter sunlight patterns. Life itself changes the atmosphere. So if the Sun passed through part of the Radcliffe Wave, that would not automatically explain any single event on Earth. It would be one more layer in a very complex story. The careful version is the more honest one. The solar system may have moved through a different galactic environment, and scientists are still asking what, if anything, that passage left behind. That caution does not reduce the wonder. If anything, it makes the wonder steadier. We do not need to exaggerate the Radcliffe Wave to make it remarkable. It is already remarkable enough. A vast nearby chain of molecular clouds was hidden in plain sight. Modern three-dimensional maps revealed it. Young stars and gas motion suggest it may be oscillating through the plane of the Milky Way. Some of the most famous nearby stellar nurseries appear along it. It may help define the gas structure of our local arm, and it places the Sun's neighbourhood inside a clearer, richer galactic landscape. There is also something deeply practical about the discovery. It shows what better measurements can do. Gaia measured the positions and motions of stars. Dust maps turned reddened starlight into a three-dimensional view. Radio observations traced molecular gas. Young clusters acted like markers of recent star formation. Each tool contributed one part of the picture. None of them alone would have been enough. The Radcliffe Wave emerged because many kinds of evidence were brought together. That is often how astronomy works now. Not just one telescope pointed at one bright object, but many surveys, many wavelengths, many measurements, all gently persuading the galaxy to admit its shape. From a human point of view, it is funny that something thousands of light years long could count as local. But astronomy has never been shy about stretching words. Nearby can mean hundreds of light years. Recent can mean millions of years. Small structure can be larger than anything human beings have ever built or crossed. The Radcliffe Wave makes our ordinary sense of size loosen its grip. The solar system, which already feels vast when we think of Neptune, becomes a small travelling point beside a structure so large that whole constellations only show us fragments of it. Yet the story also brings the scale back down to something familiar, because the wave is not only a line on a scientific plot. It includes Orion, a part of the sky many people know. It includes nearby molecular clouds astronomers have studied in detail. It includes star-forming regions where young suns are surrounded by disks that may one day produce planets. It is not just huge. It is connected to the kind of process that made our own existence possible. The Sun was born from a molecular cloud long before the present Radcliffe Wave looked as it does now. Earth formed from a disk around that young sun. Everything here, from stone to seawater to breath, comes from the old cycle of gas becoming stars, stars making heavy elements, and those elements being returned to space. Along the Radcliffe Wave, that cycle continues. Cold gas gathers, dust shields it, dense cores collapse, protostars ignite, disks form, young stars push back against the clouds that made them. Massive stars, if they form, will live short lives and end violently, returning fresh material to the galaxy. Smaller stars may shine quietly for billions of years. Some may host planets, some planets may remain barren, others, in ways we cannot know, may become interesting. The wave does not promise life, it promises ingredients, structure, and time. That is already a great deal. As you settle deeper into the quiet, it may help to picture the Milky Way not as a flat diagram, but as a place with layers. There is the main disk, full of stars and gas. There are spiral features, including the local arm where we live. There are cavities like the local bubble. There are star-forming clouds along the Radcliffe Wave. There are older stars passing through, young stars still near their birth clouds, and the Sun moving steadily along its own orbit. Nothing is isolated. Each structure overlaps with another. Each motion is part of a larger motion. Earth turns, the Moon circles Earth, Earth circles the Sun circles the galaxy, and the local gas rises and falls through the galactic plane. That can sound dizzying if we rush it. But there is no need to rush. The motions are real, but they are slow enough to feel like stillness. Tonight, from where you are, the room may be quiet, the window may be dark, the sky may be hidden by clouds, buildings, trees, or the glow of a city. Still, beyond all of that, the solar system continues its long path. It does not ask us to keep track of every movement. It does not require us to understand every cloud. It simply carries us steadily through the changing neighbourhood of the galaxy. And perhaps that is why the Radcliffe Wave makes such a good ending to this journey. It is large but gentle in its effect on our imagination. It does not demand fear. It invites orientation. It says, here is where you are more or less, not alone in empty space, not centred in a special ring, but near a great structure of gas and star formation, inside a local arm that is more complex than we once thought. It gives our cosmic address more detail. It reminds us that the sky is still being mapped, even close to home. There is a quiet humility in that. Humans have looked at the Milky Way for thousands of years. We have named its stars, built myths around its constellations, used it for navigation, painted it, photographed it, and measured it. Still, only recently did we find this wave near the Sun. That does not mean we were foolish before. It means the universe is layered, and each tool reveals a different layer. Eyes gave us the band of the Milky Way. Telescopes gave us stars and nebulae. Spectroscopy gave us composition and motion. Space missions gave us precise distances. Three-dimensional mapping gave us the wave. So if you ever feel that the universe has already been fully charted, the Radcliffe Wave is a calm reminder that even our own neighbourhood still has surprises. There may be more structures nearby that we have not yet recognised. There may be more links between clouds, clusters, and bubbles. The Milky Way is not finished teaching us where we are. It is patient. It can wait for better instruments. It can wait for better maps. After all, it has been turning for billions of years. It is not in a hurry, which is a helpful attitude for bedtime. Now, gently, let the picture widen one last time. Imagine Earth beneath you, turning through night and day. Imagine the moon tracing its quiet path. Imagine the planets spread around the sun, some rocky, some giant, some cold and distant. Imagine the heliosphere around them, the sun's broad bubble pressing into interstellar space. Around that, picture the local bubble, a larger cavity shaped by ancient stellar explosions. Nearby, beyond our immediate calm, the Radcliffe Wave stretches through the local arm, carrying cold clouds and young stars along its length. Farther out, the Milky Way curves around its centre, a barred spiral galaxy with arms, dust lanes, star fields, and many other structures we are still learning to read. And here you are, listening from one small point inside that whole arrangement. So let me ask you again, softly, as we return to the simple present. Where are you listening from tonight? Are you under clear stars, under rain, under city lights, or already half asleep with the sky far beyond the ceiling? Wherever you are on Earth, and Earth is moving beside this quiet galactic tide. You do not need to see the Radcliffe Wave with your eyes for it to be real. You do not need to measure parallax, trace molecular gas, or model the motion of young clusters before you rest. Astronomers can do that careful work. For now, it may be enough to know that the space around us has shape, history, and motion, and that our solar system belongs to a neighbourhood much richer than empty darkness. If this slow journey through the Milky Way has given you a little calm, a little curiosity, or simply a softer place for your thoughts to land, I would be ever so grateful if you liked the video and subscribed. It helps this peaceful corner of science reach other people who might also enjoy drifting off beside galaxies, clouds, waves, and questions that do not need to be solved all at once. And if you're still awake, that is perfectly all right. The universe is large enough to give us something to think about, and patient enough to let us sleep before we finish thinking. The Radcliffe Wave will continue its long motion through the Milky Way. Orion will keep forming stars. The local bubble will keep surrounding our solar system. The Sun will continue its orbit around the galaxy, carrying Earth along with it. And tonight, for a little while, all of that enormous movement can become strangely restful. Not because it is small, but because it is steady. Not because we understand every part of it, but because we understand enough to feel where we are. So rest now, fellow traveller. Somewhere beyond the room, beyond the clouds, beyond the turning Earth, a giant wave of star-forming gas lies close to our path through the galaxy. It has been there longer than any human story, and it will continue long after this quiet night has passed. Sleep well, wherever you are listening from, in this small warm moment beside a gentle galactic tide,